So, hello everyone. Good morning or good evening. Welcome to the ISDSA workshop, Introduction to Dynamic Network Analysis. Our speakers today are Professor Chow from the Penn State University, Professor Park from the University of California, Davis, and Dr. Pesigan from the Penn State University. So if you have any question during the workshop, please feel free to drop in the chat box, and we also have a transition sessions between the speakers, so you have time to ask your questions. Thanks for your cooperation. Yeah, so please join me in welcoming our speakers today.
Thank you. Good morning to those of you in morning time zone, and good evening to those of you who are enjoying your time in Beijing. I'm going to go ahead and share screen. So as the host mentioned, I'm Sy-Miin Chow, and I'm at the Penn State University. And I want to first kind of align people to the course materials shared on the course website. Let me kind of get things lined up a little bit. So we have three speakers today. I'm joined by my colleagues, Jonathan Park and Jack Pesigan, and we have uploaded our materials to the course website. So they go in the order, basically as the materials show on the current website. For my portions of the lecture, basically I'll be using PDF, and then I have some R Markdown code that you can download. So if you downloaded the notes prior to 8:59 today, you will see that I accidentally had the August 31st date on the first slide. So if you see August 31st, that is an indication that you probably need a new version of the lecture notes that you can download from the website. So here are my plans for today. Basically, what I will focus on is giving you some intuitions on why it may be interesting to use dynamic network analysis, and trying to make some brief connections of dynamic networks to a lot of models that are related, identical, equivalent, closely related, but they go by very different names. I will basically highlight the importance of doing stability analysis and touching on why that helps us understand the nature of the dynamic networks. And shortly, around 9:30 or so, I will turn things over to Jonathan, and then he will talk about finding homogeneity in ideographic dynamic networks using various variants of the package ctGIME. And then Jack will talk about mediation analysis using dynamic networks. So the idea of network analysis basically existed long before we started thinking about making the networks dynamic or applying them to longitudinal data. So here I'm including some figures from Watts and Storgas, and this is the idea of a small world network, which is a kind of network where it's basically in between a regular network and a completely random network, in that there are a lot of small triples that you can get in a small world. So they are very connected. You have high clustering, but at the same time, you don't need a lot of these paths, right? So the network is not very densely connected, and yet information can travel and get propagated very efficiently. So this idea of a small world networks is so fascinating, and it basically inspires a lot of subsequent ideas of how for imagining or modeling or representing a lot of different variables or processes, and also actors, partners, people, right? Basically as networks, and then understanding different characteristics of these networks. So today I'm going to focus on one particular kind of dynamic network based on vector autoregressive model or graphical autoregressive model. So I like this landscape idea that Hoekstra recently offered in a paper in Behavioral Research Methods. What I'm showing here is not the network actually from a vector autoregressive model, but rather is the network from the so-called Ising model. But they then compare this network to vector autoregressive model. So here's the intuition, right? So in an Ising model, which is actually a nonlinear variation of the model, right? It basically postulates that for psychopathology or people's emotions, there are often two different categorical states, healthy, unhealthy state. And then basically individuals may be fluctuating, going from one state to another. The network that we are talking about today, vector autoregressive model, is a linear network. So we don't see the two values, so there's only one value. But the idea is that the value of the value and where that is located basically can give us a sense of people's level of health, on emotion and other health domains. And then and another interesting characteristic that we may be interested in is how densely connected the network nodes are. So these different circles are the nodes of a network, and the paths are basically edges connecting the nodes. So some might say that a network that is more strongly connected, in some cases, actually correspond to high psychopathology. So when we have a lot of different emotions, but they are so densely connected such that when you are depressed, you also feel angry, anxious, and so forth, then it may be harder for you to get out of unhealthy states. So the model that we are going to be talking about, a vector autoregressive model, is related to a lot of models by similar names. But as I mentioned, unlike having the Ising model or some other nonlinear network models that have basically two values, we only have one equilibrium, right? So in this case, regardless whether you start here or there, basically you will move towards the equilibrium here, the value right here. And the strengths of the edge weights basically can influence how quickly you will get to that bottom of the valley. So if you compare basically the top panels to the bottom panels, basically the location of this equilibrium or set point are different, right? So in some cases, you may have high versus low values. So if you imagine that corresponds to emotional or affective health, for example, a higher value of health or higher level of joy, happiness, or higher value of set point may correspond to a better state, right? So that is the trait. In the long run, it corresponds to the trait level if that set point is stable, right? And it stays all the time. And then the edge weights, the absolute magnitudes of the edge weights basically control how steep this drop is. When the edge weights are very high in absolute magnitudes, then you basically get to the bottom very quickly. And compared to that, to this variation where it actually takes longer. Like if you have a ball here, it takes longer for us to get to the bottom. And then how you get to the bottom also changes depending on whether you have a univariate process or you have couple processes. So we can basically start with an autoregressive model, which is a model where we are relating a variable at time t to itself at time t minus 1. And alpha 1 is the so-called autoregressive weight. But this eta may represent within person deviations. So from our raw time series data for person I at time t, we can start by basically decomposing the data into a within person part and a between person part. So the I indexes person. So this is the set point for person I, and then this is the within person deviation from that set point. And then we say that every person basically has a stable set point, a trait level, and they basically fluctuate around this set point. And this alpha 1 basically corresponds to the edge weight, and it controls how fast someone is able to get back to the set point if they are moved away from it. So if I move a ball from here, from the bottom to here or there, how fast can someone get back to that set point? So this represents an interesting between person differences in trait level, and we can try to predict that set point using some other covariates that may possibly be grand mean center. So this is offers another view of the autoregressive process. So by altering alpha level, going from point 8 to point 3, for example, so this basically shows that when you are pushed away from the set point of 0 in this example, it takes you longer to get back to it. In the affective literature, the alpha or autoregressive weight has sometimes been referred to as inertia, right? So basically, thinking back about this, you're encountering a lot of resistance, right, in getting back to that equilibrium, that set point. And in the case of negative affect, people who have lower self-esteem, for example, have been shown by Coupens and colleagues to be showing high inertia or getting stuck in extreme negative affect states before they're able to get back to that set point. So we have seen that basically the edge weights, or in this case, the autoregressive weight, actually allow us to get a sense of the dynamics of the system, right? How fast they are able to get out of extreme states or values. And in the literature, sometimes people use the term autoregression and autocorrelation interchangeably. They are the same when you have a univariate process that is stationary. So stationary means that all the statistical properties of the processes, including the mean, the standard deviation, are the same over time. Right? But they are generally not the same. They're regression coefficient versus correlation coefficient when you have other variations, when you have higher order lag, so that the dependency is not just on time t-1, but t-2 and so forth, or if you have higher dimensional processes, multivariate systems. So now I'm going to kind of quickly highlight the connections between the vector autoregressive model to some other well-known variations. They have very different names, but they are basically special cases or they are related. The first one is the actor-partner interdependence model, or APIM model. So this part basically represents time 1 data, and these represents time 2 data. So then the path, the regression path, basically linking a person to themselves at time 2 is called the actor effects, and then we have the partner effects. Basically, this model is just a special case of the vector autoregressive model in that the couplings, or these so-called cross-regression weights, are basically constrained to be the same between the two members, right, of a dyad, or between two variables. So this is in contrast to a vector autoregressive model, where if you look at this transition matrix, the values in the diagonal, instead of being constrained to be the same, they are allowed to vary, and also the cross-regression weights can also vary, right? So this is the vector autoregressive model that basically is relating eta, the within-person deviations in variable 1 and 2 at time t-1 to their values at time t. And then the Q's here are process noises. So when we have a traditionally vector autoregressive models, basically the name came from time series models, right? So if you have intensive longitudinal data, people tend to be more used to the term vector autoregressive models. But if you have cross-lag panel data, if you have panel data where you have a lot of people that have a limited number of time points, these are panel data, panel models. People may be more used to the term cross-lag panel model. So along that line, Ricklin random intercept cross-lag panel model has gotten very popular. So this is basically the idea that you have a random intercepts or set point, and then we model basically the within-person deviations from those set points using a cross-lag panel model or vector autoregressive process. In the work of Hamaker and colleague, they basically allow the set point to be time varying, right? So for time 1, time 2, time 3, basically you can have different values for the intercept, and then you have a random effect that basically capture between person differences in set point. So Ricklin is related to random intercept vector autoregressive model. The names sound different, but basically they are similar models that came from slightly different modeling traditions. So I've already mentioned that the sort of intercepts, and the inertia or autoregressive weights can be of interest. So Coupens and colleagues basically have found, for example, that people with higher self-esteem tend to have lower inertia in emotions. They tend to basically get back to their equilibrium or set points more quickly, right? On these positive emotions. And in contrast, depressed participants were more likely to be happy, angry, and dysphoric at time t, meaning that their inertia are positive, right? And then they also so then inertia tends to be something that is of interest, like from an emotional health standpoint. So despite all these interesting findings that has shown that, that dynamic network type models and properties of these models, including inertia, that basically governs how someone self-regulates their emotion, each distinct type of emotion, and also how different emotions may be coupled to each other. One of the confound is that in the literature, sometimes the findings or the studies are designed with very different data collection time intervals. Right. So sometimes the successive occasions may be seconds apart, sometimes hours apart, sometimes months or weeks or days apart. So when we have different time intervals between successive occasions, we are basically just trying to sample at these discrete time points, right? But the magnitudes of the edges, the auto and cross regression weights basically would differ in magnitudes depending on the time intervals or the amount of times that has elapsed between two successive occasions. So when we are comparing studies across different papers, different publications, that may create difficulties in connecting the findings. And so continuous time models basically open up the possibility to kind of see how these edges or AR or CR values vary depending on the amount of elapsed time. And depending on the systems that we have and the whole configuration of weights, sometimes we may have misleading conclusions about the directions of the weights and whether we have negative or positive coupling among different processes, depending on the delta T. So the next few slides basically kind of offer some summaries or intuitions behind continuous time modeling. Right? So the idea is that we have generally a measurement model or measurement process that connects the manifest variable at discrete time tk for person I to the latent variables for that discrete time occasion. And then in the dynamic part, basically we try to represent the changes in our processes of interest per period of time, right? So per time unit. So in terms of distance, this rate of change corresponds to speed, right? Because it basically gets at how much distance has changed over 1 unit of time. So whether you're going 60 miles an hour, 120 miles an hour, and so forth, right? And this in turn is usually expressed as a deterministic part that we can basically map out perfectly once we know the previous values of eta, and then a stochastic part that basically represents process noises. Sometimes in the literature, you will see these equations being written like this, right? Instead of change per unit of time, we express things in terms of changes over some amount of time, right? And the reason is that the process noises in continuous time system basically have some interesting characteristics. In particular, we would write the change in eta basically over the time period of dt as a function of the vector of intercepts b. And A is the so-called transition matrix, a drift matrix that relate changes in eta to eta values. And then we have a diffusion matrix that basically is the matrix square root of the process noise covariance matrix. So how much uncertainty or how much we still are not able to account for, even if we know the true values of B and A and eta at time t. Then the W is basically a Wiener process, which is a kind of process noise in continuous time. So the next few slides, I'm going to skip relatively quickly, but I just want to offer some intuition on how to understand these continuous time process noise or Wiener process. Sometimes people use the analogy of someone who is drunk trying to walk around and then taking a step to the left or right, in a random manner. So to me, it reminded me of my attempt to navigate my directions in Seoul as part of the international meeting of the Psychometric Society, because my sense of direction is so bad, right? So, I could be, and I was not able to sort of read neighborhood map very well. So I may be going left or right, east, west, in a somewhat random manner. So the change, right, in Wiener process, or the change in process noise, you can think about how much my location changes. I'm like wandering around a lot, right? But a characteristic of these linear processes is that the amount of change in process noise is larger as delta t, as the time interval gets very small. So the denominator, if you want to look at the rate of change in the linear process per unit of time, the denominator basically gets to zero quicker than the numerator. So then it explodes. So then we basically write the equation in continuous time in terms of differential form, moving dt basically to the right-hand side of the equation. So I'm going to skip over some of these, but highlighting some of the key points, right? So the key point is that when we now have continuous time models, it is helpful because we don't have to make a decision on how we want to sample, right, in terms of how sparse or how much time has elapsed between two successive occasions. Sometimes we may be interested in measuring trait processes that change more slowly. Sometimes we may be measuring things that change more quickly. It's intuitive and perhaps appealing to have an irregular sampling design where we basically would sample people at different time intervals and see what works out. And the continuous time model makes it easy to accommodate these irregular time intervals. Right? So then we have basically just instead of t minus 1, we have t minus delta t representing the difference in time between the previous occasion and the current occasion. Now, the key thing that I want to highlight is that now in a continuous time model, the matrix of AR and CR coefficients now written this way basically is a function of the delta t, right? The time difference between the previous and the current occasion. And the intercept also is a function of delta t. So EA, this is basically taking the matrix exponentials of A, right? So for those of you interested, you can basically do that by approximating it using this power series function. So we have basically polynomial functions, and then this is factorial. Or you can get matrix exponential by calculating the eigenvalues and eigenvectors, and then exponentiating the eigenvalues of x. So in general, right, how does the autoregressive weights, right? So these are the diagonal entries basically in this drift matrix. How do they change as a function of delta t, as the amount of time that has elapsed? Generally, they are the highest, right, or strongest in magnitude in absolute sense, right, when you have smaller delta t, right? So when you measure a process more closely in time, you're able to get stronger stiffener in terms of inertia and the coupling from one process to another, which is appealing. But on the other hand, right, we can better get at the set point if we have larger delta t. So if you're sampling a process that is changing and fluctuating around the set point, and you're trying to get at a asymptote, trying to get at the stable value of this process, then you kind of need larger delta t to be able to capture that well, right? So again, irregular designs kind of give us a balance in that we can try out different time intervals and see how that works out. So in continuous time then, basically we have something that looks like this, right? So we have the change in eta. So in this case, eta is the vector consisting of two within person deviation variables, eta1 and eta2. And we are basically modeling those changes as fluctuations around a set point, a set of set points for person I, right? So in this case, I should have the I index here if you want the set points to be person specific. And then we have an A matrix here, and this minus sign basically is to highlight the fact that when we go from discrete time to continuous time, the sign in this particular representation got reversed. So in discrete time, I basically wrote this as eta t minus set points. So the reason is that now if you want to turn this continuous time equation, which gets a change into discrete time, we basically have to write that as eta at time t, or eta as time t being a function of eta at time t minus 1 plus the change. So the fact that the change gets attached to the second part, it reverses the sign, right? So now I write it like this. The set point basically goes in front, and then the transition matrix, right? So the discrete time matrix of AR and CR basically now is the negative of the weight. So I have this negative sign here, right? So I have the intercept, right? And I have basically the transition matrix A, and then the diffusion matrix that basically governs the standard deviations of the process noises. Now, the key thing that I want to highlight here, which I provide more code and annotations in the R Markdown file dynamic network analysis, is the following, right? Regardless of whether you are modeling in discrete time or continuous time, it is helpful to understand the stability of the system, right? So the stability of the system basically makes sure that when you have the ball rolling into the valley, you have a valley. The ball eventually gets to the bottom of the pit or the equilibrium, the set point, as opposed to having a peak or a hill, right? Where it basically moves away from the top of the hill rather than going towards it, right? You can't stay at the top. Whether you have discrete time system or continuous time system, it is important to do that, right? So the key way to do it, so I explained that in more detail in the R Markdown code and the corresponding needed HTML. And my colleagues in a few minutes will share basically code that automates some of these process model fitting so that you don't have to work with matrix exponential yourself if you don't want to. So in this particular example, which basically is an excerpt from the R Markdown code that I just showed, it basically shows how you can use the var function from the vars library to fit a model. And then here I'm specifying a leg of order 1. So I'm relating basically eta at time t to eta at time t minus 1 only, right? So I'm not going leg order of 2, so I ignore dependency on time t minus 2 and so forth. And I'm basically including an intercept for the deterministic portion of the change. So once I have the leg1 transition matrix, so this is the matrix that has the AR and the CR weights relating eta at time t minus 1 to eta at time t. I can then basically check for the stability of the system by calculating the moduli, so the absolute values, if you have eigenvalues with real values, just checking to make sure that the moduli of all of the eigenvalues of this transition matrix basically are less than 1 in values, right? So for those of you who may need a refresher of eigenvalues, or if eigenvalues and eigenvectors are not your friends, you can generally think of eigenvalues as determining how much a system is stretching or expanding or contracting. So in this case, if they are contracting, basically you have a stable system. So rather than having means and variance that may explode over time, you have finite values. In continuous time, basically you work with the matrix A that is in the continuous time model that I just showed you, right? So basically, we can do an equivalent test by checking for the eigenvalues, in particular, the real part of eigenvalues to make sure that they are negative. And then if you have complex eigenvalues, so this is having the imaginary number square root of I, then basically you have oscillations. So instead of having that ball rolling down into the valley, now imagine that, for example, if we have a bivariate process, we have dependent variable 1 and 2, right? And in some range of the parameter values, we may get negative eigenvalues, right? So this will basically show up as imaginary numbers of I, right, in the R output. So what happens here is that you can still get a stable system, meaning that the thing is still curved downwards. So if you have a ball on this landscape, it will still roll down towards the set point or equilibrium at the bottom. But it does not do so in a monotonic fashion, so not in like exponential decay, like going down in one direction, but rather the ball kind of rolls around and spiraling downwards before it hits the bottom, right? So this is important because sometimes, we may see in our drift matrix, right, when we fit continuous time models or discrete time models, that the coupling weights may not be in the direction that you expect. But by looking at the stability and trying to understand the eigenvalues, then it helps shed light on in what ways the system regulate or move towards equilibrium or set points, if at all, right? So whether they spiral downwards this way, like a ball spiraling downward, or they kind of go straight down to the equilibrium. So the needed version of the code, see. All right, here I will leave the code and the annotations to you because my colleagues will highlight other coding examples that make this process easier for you, right? So this basically highlights how we can get discrete time models in the form of a VAR process, right? And then getting the eigenvalues and the moduli of the eigenvalues. What happens if you have higher leg order, and then basically talking through continuous time models, what the intercept means, and how a system can kind of regulate towards some set points. And then if you're interested in my navigation pathways in Seoul, right, here it highlights some properties and characteristics of the dynr process of continuous time process noises. And then it now talks about a stability analysis in a continuous time version of the autoregressive model, the Ornstein-Uhlenbeck model, using values from a published paper. And it basically allows us to extract, for example, the real parts of the a set of eigenvalues and check whether all real eigenvalues are negative in values, right? So this, again, spoken in a different way, make sure that when you shock a system so that the ball rolls away from the valley, whether that shocks basically dissipate over time, so you get back to the bottom versus you kind of move further away from that valley. And then you check whether your eigenvalues contain imaginary numbers, right? So this tells us whether we have straight pathways towards the equilibrium, or basically we do that in a spiral fashion. And finally, Jack will talk about basically formulating some of this model as continuous time state space model, which basically requires that we have a measurement model. So I am going to basically stop here and turning things over to my colleagues. Some key points that I want to highlight. So the off-diagonal or the cross-process coupling entries in the transition matrix, right, whether in discrete time or continuous time, generally constitute the edges that connect the nodes in dynamic networks. My colleagues will talk about how to extract those edges and create fancy, nice-looking plots. Right? A lot of these applications typically ignore the signs of the edges, right? Whether you have positive versus negative ones. Some other applications find that substantively meaningful, right? So that is something to think about. Both in discrete and continuous time, it's important to think about how to handle random intercepts if different people have different set points. It's important to acknowledge and accommodate that. If you have trends, right? If you have changes in means or set points over time, it is also important to accommodate or address that or remove the trends prior to analyzing the dynamic networks. Stability analysis checking is important because it tells us whether we have that valley instead of a hill, right? Whether you have convergence towards some set points or you get progressively crazy and moving away from my a set point, right? And then irregular design is basically, it's helpful, right? So that we don't have to worry about whether we have spaced out the processes enough that we can capture the set points, right? Versus also capturing the inertias and the couplings at reasonable, meaningful range of values. All right. So I'm going to leave you guys with additional resources and source code for other modeling variations. And then here are some of the modeling options that Jonathan and Jeb will talk to you guys about with references. So I'm going to stop here and let Jonathan set up and see if anyone has any questions.
I can share, but I don't know
Okay,
if we want
yeah.
to wait a second.
Yeah, people are very quiet. I think you can go ahead and get ready to share. Yeah.
Yep, indeed.
Okay.
Um, Thank you so much, Sy-Miin, for
Go
covering all the
for it. Yeah,
background.
Jonathan.
Okay. Hello. I am Jonathan Park. I'm an assistant professor at UC Davis. And it was 6 a.m. when this started. I'm on the opposite end of Sy-Miin, where instead of staying up all night, it's just very early. But luckily, the jet lag from Seoul is helping me because I think it's like 9, 10 p.m. there now. So I feel kind of okay. Like I took a nap in the middle of the day. I know that if one were to look at our workshop materials, and if you go to my workshop materials, it's kind of a nightmare. So what I would advise if for people that would like to follow along either in the slides or in the Quarto document or the results that we'll go over in my portion of this, if you click on the folder and then you click on the folder again, if you just download the whole folder, you'll get a directory. You can see that I've already tested this. Um, you'll get this whole directory that has all of the files in order. I will start going through this PDF, which is the presentation, and then in this Quarto file, you'll see all of the actual code that we'll be running. So everything else is output files. I've basically pre-run this because continuous time gimme models can take a long time to run. And so I've just kind of done this part for you. Obviously, if you would like to run this on your own and just validate that my code actually works, feel free to. There are sections that have been set to not evaluate when you knit the document, but if you turn those on, then it will run. I will be running it so that people can see like the status messages that you get when you run continuous time gimme, and I'll be talking about a little bit more of the kind of background technical aspects should you choose to use this in your own work. Also, just as an additional note, as someone who is on the tenure track, if you would for whatever reason like to collaborate, feel free to send me a message. Um, right. So my portion of this talk is on continuous time gimme models. Actually, one second. I do need the chat to be open just in case. So if people have questions, do feel free to put them in. For code related things, particularly, I imagine that some problems could come up. So do let me know. So this kind of set of slides they're adapted from another talk that I gave when I first developed the subgrouping extension for continuous time gimme. So in this portion of this talk, you'll basically hear a mix of the motivations of modeling in continuous time, unsupervised model building, and this idea of how do we address the idea that our samples are not always homogeneous and the degree of heterogeneity in our samples is not always something that we know. So can we leverage information that the subjects give us in their time series to automatically identify who belongs into what kinds of subgroups? Um, so just to like orient us in terms of what we'll be talking about, I'm going to be talking about modeling in continuous time. Luckily, Sy-Miin has done a fantastic job kind of setting the groundwork for that. And then I'll talk about this idea of undiagnosed heterogeneity and why it becomes more of an issue when you model this stuff in the continuous time framework and potentially less of an issue when you model it in the continuous time framework. I don't know if I said that wrong. If you model this in the discrete time framework, it could be more problematic than if you do it in the continuous time framework. Then I'll talk about continuous time gimme, a little bit of the technical aspects, and then show you some preliminary simulation work that we've been doing, particularly related to this idea of finding heterogeneous subgroups in samples of multivariate time series. Just out the gate, the problem statements of this particular line of work that I have is that one, discrete time methods are very popular, perhaps by far the most dominant form of time series analysis that we're doing in psychometric or in psychology. And contrasting to this, continuous time methods may more accurately reflect how we perceive constructs, right? So when we think about my emotions, when we think about my depression, we might envision that this exists as a persistent state, regardless of whether I measure it or not. And so modeling this process seems to align more closely with continuous time methods rather than these discrete time approaches. And on top of that, this idea of within sample heterogeneity that I keep touching on is addressed quite well in the discrete time literature, but significantly less well in the continuous time literature. So there's less methods, there's less approaches, and so necessarily you have less options. And so there's a lot of work to be done and a lot of work that can be done. And so researchers are often interested in this idea of identifying heterogeneous subgroups. I know that there are subtypes, for example, of this particular disorder, and I want to find those. And modeling this heterogeneous group as one monolithic group can result in biased estimates or false positive edges that you might pick up. And in addition to that, I don't want to maybe necessarily model each person as an individual process, because if there are commonalities in the data set, I want to be able to leverage that information to help me pick up estimates in other people, but I don't want to place unnecessary constraints. So I don't want to assume everyone's the same, but I want to use information when that information is present, right? So if you and I share paths, we should probably pool our information to pick up that and increase our power. But if there are paths that we do not share, we don't want to unnecessarily constrain that path for you or for me. So it's an interesting problem that we have. And so then this is kind of going to transition to this idea of our theory and our models. So we have continuous theories, or at least in psych, we like to talk about things as persistent things. So my depression is a persistent phenomenon. But we often model these things discretely. So this blue line or this blue time series is going to be this continuous process that is unfolding. Because I always talk about depression, I'm going to just keep using that. And so with depression, you can imagine that I have some baseline level of depression. Sometimes I am a little bit more depressed. Sometimes I'm a little bit less depressed. And this is something that is always happening, regardless of whether we measure it or not. But then, in contrast to that, these red dots are the realizations of that time series, right? So this is when I would be gathering my data on when you're depressed. And so the red dots are our realization of the time series, whereas the blue dots or the blue line is the continuous time series that we're assuming exists. And you can imagine that I can shuffle these red dots. I can sometimes put the red dots more frequently. I can sample more frequently. Other times I can sample more slowly. And as Sy-Miin noted, and as I'll talk about, sampling faster or slower in a discrete time framework means that the temporal relations that we have are going to be different. If you think about something making you angry, if I'm angry right now, 5 seconds from now, my anger 5 seconds ago is probably strongly predictive of my anger right now. But then if we sampled me, let's say every day, how angry I am today might not be as predictive of how angry I am tomorrow. And so the effect of the lagged association is time dependent, or at least sampling interval dependent. And this led me to talk about or think about what happens when we try to find subgroups in continuous time models or in discrete time models. So when you fit a discrete time model to a continuous process, as I've noted, we can basically look at what the effects are at these different sampling rates. So if I model the exact same process, it is generated from an underlying continuous time process, but I discretely subsample it at different intervals, then I'm going to find that there are different associations in terms of magnitude between certain constructs. So in this case, this is simulated data. My sampling rates are technically arbitrary, but we'll label these as being every 12 hours, every day, and every week. And so if I subsample my continuous process every 12 hours, every day, or every week, I will see that at the 12-hour lag, my depression and my anxiety have strong autoregressions. And so there's a lot of continuity in these variables. And there's a relatively weak effect between depression and anxiety. So from right now, how depressed I am does predict my anxiety 12 hours from now, but that effect is relatively weak, and most of the effects are in the autoregressive dynamics. If I sample every day, we see that that cross regression has increased in strength. So apparently, for this simulated case, the effect of depression increases over a longer period of time, but over a course of a week, when you feel depressed, it becomes pretty much non-significant. The effect of your depression on your anxiety a week later, on average, tends to be quite weak. And so we can see that just because we sample at different effects, this is the same time series that I simulated, just because we sample at different sampling rates, we're going to see different effects. And this doesn't mean that we're modeling or picking up a different process. This is just a different point in that relationship that is always happening. And this led me to develop this idea that I'm calling illusory homogeneity. And so in this case, I've simulated two time series of two people who have different data generating continuous time models. And the idea here is that if I were to cluster or subgroup people based off of their cross regression dynamics, I might choose to cluster people based off of whether they have cross regressions that are significantly different from zero and maybe whether they have the same sign, right? So if you and I have a negative connection from depression to anxiety, we are similar. But if we don't have that in common, we are different. And what you can see here, it might be a little bit faint if, particularly if your monitors are small. I mean, I have a large monitor and I can barely see it, so I acknowledge this limitation. Is this effect of depression on anxiety is about 0.2, and the negative effect of anxiety on depression is about minus 0.1. And for the other subject, it's about 0.1 from depression to anxiety, but 0.2 from anxiety to depression. So if I'm only looking at the sign and not the magnitudes, I would actually say at a 12-hour sampling rate, these two individuals have common or similar dynamic patterns. There's a positive effect from depression to anxiety. There's a negative effect from anxiety to depression. Likewise, if I fit this at a delta t of 1 or at a daily sampling rate, we see that there are more prominent effects, but generally there's still a positive connection from depression to anxiety, a negative connection from anxiety to depression. But at the weekly interval, I would see that basically the effects for the first subject have decayed to zero. There's basically no association between anxiety and depression. But for the other subject, there's increasingly strong association from anxiety to depression. And so if I were to subgroup these same people using the same data generating processes, albeit different, I would say they are possibly the same group, and then the different group. And this is problematic, right? So if I'm trying to find subgroups, I would imagine that my idea of saying two people are in the same group is time invariant. I would want to say you are in group one with Jack, and that is something that is always the case, rather than saying, well, on a weekly level, you and Jack look the same, but on a daily level, you and Jack look different. And so we want to cluster people based off of something that would be more stable. And in this case, the continuous time dynamics that you recover should be relatively invariant to sampling size or sampling rate, and so would be more attractive for this case. Just some background that I can thankfully kind of skim over a bit is I've been talking a lot about discrete time models and continuous time models, and I want to orient us to the particular models that I'll be talking about. So in this case, we have the discrete time vector autoregressive process. So this is a VAR or a VAR of lag order 1. So I'm only looking at the previous time point affecting the current time point. As Sy-Miin noted, our kind of vocabulary is that there are autoregressions, the effect of variable 1 on variable 1, and variable 2 on variable 2. And then we have cross regressions being the effect of variable 1 on variable 2 and variable 2 on variable 1. So we have cross regressions and we have autoregressions. The equation for this is basically, as long as you're familiar with linear regression, you should see the common allegories to this, where we have something that we're predicting is equal to our intercepts and our regression coefficients matrix times something else, right? So usually in regression, we have y predicting or predicted by x, but in this case, we have our scores at a given moment are predicted by our scores at a previous moment. So as long as you're familiar with linear regression, you can make the adjustment and kind of pick up, okay, this is just saying how do my variables right now get predicted by my variables some arbitrary lag ago. And in psychology, particularly, our applications generally kind of reduce down to lag one. So in this case, you'll see this most often where it's eta at t being predicted by eta at t minus one. In continuous time, as Sy-Miin kind of showed us already, you have a different set of equations, and I'm not going to go into the annotation of this, but one thing that I would like to note is, given that I've just pointed out the similarity between this equation and linear regression, if you look at this equation, you should also see the elements of linear regression, right? So we have change in our latent states, so change in our etas at a given moment, and then our regression coefficients matrix and our eta, so our scores, the levels of our scores at a given moment. And so rather than having a discrete step in time, we have this kind of continuous association between the variables. And then we also have our process noises and our innovations. And despite the fact that these are different models, they are quite intricately tied and connected to one another. And so in discrete time models, such as the var, parameters, as I've mentioned, are dependent on your sampling rate, and they generally want you to have equally spaced data, right? So if we go back to this equation, the idea is that eta at time is predicted by eta at t minus one. And as we try to recover and estimate this phi matrix, if your eta at t minus one is actually eta at t minus 0.5 sometimes, and sometimes it's eta at t minus 2 or eta at t minus 1.7, if that keeps changing, then the estimates that you're going to get on average in phi are going to become biased. And so ideally, when you say that I'm having a lag one regression between previous time points and current time points, you actually mean that, and that your sampling rates are relatively consistent. I will note that sometimes it can be okay if you have a really, really long time series, and if you're randomly sometimes late and randomly sometimes early, it does average out. But for most purposes, you're never really going to have enough time points such that that averaging occurs. You will usually be biased in one way or another. Likewise, there are known transformations that relate continuous and discrete time models to one another. And so any continuous time model can be translated into a discrete time model, but that opposite is not necessarily always true. So not all discrete time models are continuous time models. And so this is some line of work that I've been working on recently. And so continuous time models can be interpreted at different sampling rates. And so we can kind of demonstrate, oh wait, what the heck happened here? Yes, so we can kind of demonstrate this equivalence. Sy-Miin has already shown these equations, but we can see that if we wanted to see our discrete time regression coefficients matrix or our transition matrix for a given sampling rate, we would apply the matrix exponential to our drift matrix times the sampling rate that we're interested in. So if I wanted to, and the way that I generated these graphs, is that I had one particular continuous time drift matrix, and I said, okay, if I take the matrix exponential of this and I multiply it by 0.5, this is the graph that I would get. But if I took that same drift matrix and I applied the matrix exponential and I multiplied that by 7, then I would get this set of effects. So these transformations can give you the regression coefficient or the transition matrix of your dynamics at a particular discrete time interval. And likewise, that exists for your process noise innovations. So if you want to follow through with these equations, you can basically get what do my covariant or my process noise covariances look like? What do my discrete time dynamics look like? Just to kind of illustrate this more visually for folks, because sometimes equations can be daunting, I have a true A matrix here and a true process noise covariance matrix in continuous time. And if I take this set of effects and I apply the matrix exponential and I multiply that by 1, what I get is this set of dynamic coefficients. So you can see that I have positive effect between variable 2 and variable 3, and then I have negative effects between variable 3 and variable 1, and variable 1 and variable 2. When I exponentiate this, what we see is that that positive path is still there. But I've also gained an additional phantom path that Jack will be talking to us about. I get an effect between variable 1 and variable 4 that is weakly negative. That is not in the continuous time process, but it has emerged in the discrete time realization of that continuous time process. And if I exponentiate the same A matrix to an interval of 10, we see that these effects are largely near zero. So it basically over the course of this sampling rate over a course of about 10 units of time, all of the effects, all of the relations tend to decay to zero. By contrast, in my process noise innovations, I just have identity for my process noise covariance in continuous time. And as I apply those transformations, we see that we obtain relations, or what we would call in discrete time, our contemporaneous effects or shocks between our variables that appear as a function of the distance in time. And so ironically, as our dynamics kind of decay over time, the information in our process noise covariances increases over time. And so at slower sampling rates, we see stronger covariances between our variables. And so we see basically information in our dynamics goes down, and then information in our process noises increases. And this will be relevant for some of the simulations that I'll talk about shortly. So just to recap, because that was a lot of math, so continuous time models theoretically probably align with how a lot of us think about processes. I keep using emotion and psychopathology examples, but you can imagine that a lot of processes probably continue existing, whether we measure them or not. And so just treating the observed realizations of these processes as being the things that we model seems to not really align with what we're thinking. And likewise, discrete time models have several limitations that are addressed explicitly, by continuous time models. So the effects that they obtain are dependent on your sampling rate. They are sensitive to unequally spaced measurement occasions, and there can sometimes appear to be similarities between people, even if their data generating processes are different. So just because I happened to sample you at the right time, you might look the same, and that might not be what we want to do. So a second kind of tangential but related point to this is that we want to balance the group and the individual. So models that we use imply certain assumptions that we have about the real world. So we might have questions about how much heterogeneity is there, or what is the form of the heterogeneity that we're modeling. Sometimes we might think that heterogeneity is something that is continuous variation about a true process. And other times we might think that the variation is discrete, that there are real different groups of people that are qualitatively different in some way. And regardless of that perspective, the question arises regarding these challenges of how can I leverage information from other people without placing unnecessary or strict constraints on individuals. So I've kind of alluded to this earlier, but if Jack and I share some information, it would be really useful to pool our information to get our estimates. But if there are paths that Jack has that I don't have, I don't want to leverage that particular information. So I want to pool information when it's helpful, but not pool information when it's not helpful. I like to think about this in terms of an idiothetic spectrum of methods. So on one end, we have idiographic methods. On another end, we have nomothetic methods. Idiothetic was coined by, I think, Allport in 1937 for personality research, but then I am stealing it now and we're using it for methods. And so we can imagine on the purely nomothetic side, we have this idea of everyone is interchangeable. We can fit one, let's say, fixed effects model to every single person, and we can just pool all of the information in our sample. If we're willing to say that everyone's the same, we can just pool all of the information. And then on the other hand, we have purely idiographic models. In that case, we're saying everyone is totally unique. They share no information, or at least no useful information, and they should have their own specific or person-specific model. And in the middle is probably where a lot of us probably exist. We have our mixed effects models, we have our gimme type models, we have cluster-based methods. In this kind of middle region, we have basically methods that want to use information when we can, but not use information unnecessarily on people. And the continuous time gimme that I'll be discussing shortly is one of these idiothetic methods. So this problem of undiagnosed heterogeneity, researchers often want to find these subgroups in their data, but they might not have a priori knowledge of what those subgroups are. So with things like depression, with things like ADHD, we have theories that there are subtypes of these disorders, but maybe we don't know concretely, particularly in complex networks, what are the specific features that delineate one group from another. So if we could let our data tell us that, that would be particularly useful. Um, and so the discrete time framework has a lot of approaches for handling this. There's like the gimme approach, there's the subgroup chain graphical var, alternating least squares var model, dynamic mixture models, among a host of other methods. But by contrast, few, if any, methods exist for doing this kind of undiagnosed heterogeneity in the continuous time literature. And then, oops, I keep hitting up, and apparently up means skip up 5 slides. And so by contrast, there are very few methods that exist for doing this in continuous time. And then I made this joke when I gave this talk previously, but until now, and then there's roaring applause from the audience, and then everyone's very happy. But we have basically a continuous time extension of the group iterative multiple model estimation procedure. This was developed by Katie Gates and Peter Molinar. The first paper was in 2010, but most people cite 2012. And this particular paper or this particular algorithm is a discrete time method that identifies relations between variables that are shared by a majority of individuals in the sample. So this idea of if I look at everyone and I find that most people tend to have this path, then it might be safe to assume that that is something that everyone has. But if there are paths that are less popular, then maybe I won't force everyone to have that particular path, and I'll leave it to the individual data to inform the selection of those paths. And in 2017, there was an extension that enabled subgrouping in gimme models in the discrete time framework. And recently, gimme was extended to the continuous time framework, and in this particular set of slides, we are also extending this to the subgrouping domain. So just some background for how continuous time gimme's algorithm works. So basically, continuous time gimme models models each individual using the continuous time analog for the first order var, or the Ornstein-Uhlenbeck process. And it's been shown to outperform discrete time gimme across different combinations of effect sizes and sampling rates. The general algorithm is to fit a null model or a model that's relatively empty. And what we do is we basically iteratively assess the modification indices of individual models. We pool the information from this modification indices, and we identify which particular parameter in the dynamics would substantially improve model fit for a pre-specified majority of individuals. And if there is a parameter that would improve the model fit for most people, then we add it. We force everyone to have that parameter. And we repeat this again and again until we find that there are no longer any parameters that would substantially improve the model fit for the majority. Then there's a pruning step where we remove paths that we added that may have no longer been statistically significant for a majority of people. And if we were talking about just regular CT gimme, we would then just pass it to the individual search. So then individual models will be constrained to have that group level model that we discovered. And then they will add parameters that are person specific using the same modification index based approach. With this new extension for subgrouping, we basically have an intermediary step. So what we do is we do the group level search. Then once the group level search has stopped, we search for commonalities and dynamics, and we subgroup based off of those similarities. And then we repeat the group level search, but within the clusters that we've identified. And so then we might say, okay, well, certain people or everyone shares the A to B connection. And then once we split people into subgroups, we find that subgroup 1 has a C to D connection, whereas subgroup 2 has an A to D connection. And then we'll repeat that all the way through until there's no longer paths significant for either of the subgroups. And then we can pass it on to individual level model fitting. Throughout all of this, there are procedures for correction of family-wise alpha, as well as different forms of model selection. But we'll only be talking about one form of that today. And so this extension for ctGIME, we can talk about a little bit more specifically. The way that we do the community detection is we create an adjacency matrix that I'll call A. I realize that I'm repeating A from earlier, but this is a different A. And it's created using a twofold process. So we look at paths added during the group level search that are statistically significant for an individual. And then we also look at paths in the modification indices that, if added for this person, would be statistically significant. So then we're basically creating an adjacency matrix where the cells, so in this case, the cell Aij, represents how many dynamic features the ith individual and the jth individual have in common. And these can be paths added during the group level search, but these can also be paths that the subject wants to have given their modification indices. And so we have paths added and paths that could be added, and then those represent cells in this adjacency matrix. And so in this simulated, very clean, cute case, we have very clear separation between these groups. We have a clear set of 4 people that have a lot of things in common. We have another set of 4 people that have a lot of things in common, but then person 1 and person 5 have nothing in common. And so that's how you would interpret this adjacency matrix. Then, akin to discrete-time GIME, we apply this walk trap algorithm that conducts a subgrouping search across this adjacency matrix to identify subsets of individuals who have more dynamic features in common with each other than they do with people outside of the group that they're assigned to. So just a second recap. In this case, the selection of a model implies a certain perspective of how individuals differ from each other. And while we balance this group and individual level inference, we also might be interested in identifying subtypes of individuals. And so while most approaches exist in discrete time, this is one of the first for modeling and finding subgroups in the continuous time framework. So we have one simulation that we'll talk about, and then in the remaining time that I have, we'll go over our quarter document. So I did a small scale simulation. This is actually quite large now. I did a simulation study basically assessing the cluster accuracy of continuous time GIME models. And so what I did was I simulated continuous time processes. I simulated different numbers of subgroups, and then I basically evaluated how often do we pick up the correct number of subgroups, and how does this compare to the existing discrete time GIME. And in particular, I wanted to pick up on this idea of the sampling rates. So I talked about this illusory homogeneity earlier, that sometimes I would do better, sometimes I would do worse just because of when I sample. And I wanted to see if that effect would emerge. So that's really our primary motivating question here. The design of this simulation, we have 60 people. They're divided into 3 evenly sized groups of 20 people. We have 6 variate time series. I generated 100,000 time points at a sampling rate of about 0.1, and then I would subsample that time series. Each group possessed 2 unique cross-regressive effects, and the effect sizes were based off of what they would look like at a discrete time interval of 1, plus or minus 0.2. So these are relatively weak effects that we're trying to pick up, and then we're varying the sampling rate. So we subsampled at, again, using kind of a day analogy, every 12 hours, every day, and every 5 days, up to 200 time points. So there's a confound that exists here that isn't directly addressable, but the idea is, since I simulated so many time points at a small interval, when I sample at a delta t of 5, I'm getting much more of that time series. By contrast, if I only get 200 time points at a delta t of 0.5, I'm actually sampling a much smaller window of available time. But this is just to constrain that t would be the same. We are currently running simulations where this is fixed and we unbound this. And in this case, the performance you'll see is different because you have more time, basically. And our performance is just based off of cluster accuracy, right? So I know that there are 3 groups. I know the group membership. And so now I just need to evaluate how well does continuous time sgimme perform? How well does sgimme perform, the discrete time version? In this case, the adjusted rand index is our metric, and it ranges from 0 to 1. 0 responds to chance accuracy. So 0 can still be not bad, but we need to be higher than 0. 1 corresponds to perfect accuracy, and 0.7 corresponds to an acceptable bound for accuracy. In our results, basically, the left-hand column is the results of continuous time sgimme. The right-hand column is for the discrete time sgimme. And then the rows represent the sampling rates of every 12 hours, every day, and every 5 days. And one thing I'll note is that there's a spike that you'll see in the continuous time gimme results. In these cases, these corresponds to places where continuous time gimme is consistently saying there's 2 groups when there's actually 3. So there is a notable conservative bias in continuous time sgimme. However, the discrete time sgimme on average performs quite poorly across all of the sampling rates. If we are to look at the average ARI, or the the average cluster quality, we see that at a 12-hour sampling rate, metaphorically speaking, we have an ARI of 0.61. At a delta t of 1, we have an ARI of 0.81, and at a 5 delta t, we have an ARI average of 0.72. By contrast, discrete time gimme has an ARI of, on average, of 0, 0.23, and 0.52. So what this suggests is that the subgroup accuracy, relatively speaking, is more consistent for continuous time sgimme than it is for discrete time sgimme. So when I sample, has less of an effect on continuous time gimme than it does for discrete time gimme. One thing you should notice is that discrete time gimme is slowly getting better, right? So the slower I sample, the accuracy is improving. And in previous work that I've done with Sy-Miin and Peter, we basically tested a sampling rate of 10, and we found that that discrete time gimme actually does do quite well when you sample relatively, like, very slow. And so that is something that is ongoing, but essentially, if you're uncertain about this kind of interval placement, if you're sampling fast or slow, continuous time gimme is much more consistent over the range of sampling rates that we're testing. To put this in another way, we're basically just looking at how many of the Monte Carlo replications were above this 0.7 threshold. And we see that about 30%, 70%, and about 50% were above the threshold for continuous time gimme, whereas for sgimme, 0%, 1%, and 20% were above the threshold. So continuous time gimme is consistently overperforming compared to discrete time gimme in terms of identification of subgroups with relatively weak effect sizes. So just some general conclusions. Continuous time gimme can identify homogeneous subgroups of individuals in otherwise heterogeneous samples, and effects were relatively consistent across a range of sampling rates at effect sizes commonly seen in psychological data. So these were like 0.2 in magnitude. And it consistently outperformed sgimme and did not exhibit markedly different cluster qualities. So it was relatively consistent. Some limitations are just we were doing more testing. There's a lot of testing that we're doing. And so if people do choose to try this out, we do welcome any comments and advice and feedback. This QR code, obviously you don't need to scan it because you will have the materials, but this links to my GitHub repository and has the most recent up-to-date version of Gimme. We are working on an R package, but as we're kind of testing and toying with the algorithm for subgrouping, we're not particularly rolling out the package yet, but you're easily able to just clone the repo or just get the continuous time gimme R script from my GitHub repo. But eventually there will be an R package. Most of the documentation is done. We're just kind of working out some final bugs. To transition to the actual kind of code tutorial, I want to orient people in case they have the folder but maybe don't know what to click on. So in this particular case, let's see if I can make this obnoxiously large. If you've downloaded the zip file, you will navigate over to this Quarto file folder. And within there, you would click on the ISDSA JPark26 HTML file. And this will be the file that we kind of work through. And then aside from that, there's also the Quarto markdown file. In this case, this has the raw code. So I'm going to have both of these open in parallel because I intend to run some of the code. That way you can see some of the status messages. But for the most part, if you're following along, the HTML file is sufficient. So I'm actually going to make, I'm going to make this very large. And then we will pull up this as well. So I will be switching back and forth between this and this. So I hope that's not too distracting. So the continuous time gimme script has multiple R packages, R functions. If you use this with the Quarto document, you'll see all the packages that you need. Transitioning here, you can see I have a list of packages, including OpenMX, Matrix, QGraph, Gimme, Expim, and GIFSKI. So then if you run these two lines, it will just read those in if you have it. Otherwise, you will need to install those packages. Just to, again, orient us, the things that we'll do in this tutorial is detailing and summarizing key functions and their purposes. So we're not going to go argument by argument, but we'll see what the big functions are. I provide us all with code for generating ground truth dynamic networks. We will visually demonstrate the relations between continuous time and discrete time dynamic network models, and then I'll demonstrate how to fit the simulated data in continuous time gimme. So there are some necessary functions here. I'm not going to go into the individual arguments in the code, but basically there are two functions here, being generate a drift matrix, so generate that dynamic set of parameters that also does a stationarity check, as Sy-Miin importantly noted. And there's also a function for generating the time series using OpenMX. So then here you generate time series, you select the amount of times you want, the sampling rate that you want, you provide your process noise innovations, your measurement errors, etc. Finally, there's also this source link to the GitHub repo for continuous time gimme. As you can see, we are on version 0.0.6. So make sure you get that version of continuous time gimme. If you just run this line, you will have all of the supplemental R code and functions that are proprietary to that. In the future, of course, just visit the GitHub page and then you will always be able to pull the most recent version. And then maybe in a couple months, you'll see it on CRAN. So the first step is generating our ground truth dynamic network. So in this case, we want to relate the data that we're simulating to the slides that I just presented. And so what we're going to do is we're going to generate dynamic networks of 5 variables comprised of 20 subjects. We'll have 2 subgroups where the proportion of subgroups is a 50-50 split. So there will be 10 people in group 1, 10 people in group 2. 10% of the off-diagonal edges belong to all subjects. So these are group level paths. 15% of off-diagonal edges will belong to specific subgroups. And then P individuals set to 0. So in this case, there are no unique edges for any individuals. If we turn this on, individual subjects will have person-specific paths in addition to the group and subgroup level paths that they have. There's a mean effect size that we want for our dynamics and a standard deviation applied to that. So let's say I want an average effect size of about 0.3 with a standard deviation of about 0.03. So then we'll have some range of effect sizes. And then this df is the diagonal effect size or the effect size of our continuous time analog for the autoregressive coefficient. In this case, it's set to 0.6. You would use a positive number here because my function automatically just inserts the negative for you. In this case, this is a relatively strong autoregressive effect, and then our cross dynamics are relatively weak. So once we run this function, we should get a set of drift matrices. So I'm actually going to run this code up to this point, and then we will run x, and then we can evaluate x. And what we'll get from this function is, I realize this might be small for people. Oh no, I can't zoom in. Please just get really close to your computer screens. You get output of the group level structure. This is the structure that every single person has. Then you have the individual models for subgroup 1 and subgroup 2. So this is what paths do subgroup 1 members have, what paths do subgroup 2 members have, and then you also have all of the individual models. So in this case, the subgroup models and the individual models are going to be aligned perfectly. But if you had said, I want some proportion of individual paths, then the individuals will have additional paths on top of their subgroup structure. So that's what you get when you run this X object to generate your drift matrices. You have a bunch of drift matrices. You know that they're stationary and they're all nice and good. Then we're going to simulate our time series. So we're going to use this tsgen function that I wrote. You insert the output of this X function. So it will generate drift matrices for the number of subjects that you simulated. How many times do you want? So in this case, I want 200 time points at a sampling rate of 1 interval. Our continuous time process noise, in this case, we're going to set that to just be diagonal. And our measurement error variances, our measurement error variances are near negligible. So we have almost perfect indicators. In this case, if you provide scalars, then I automatically turn it into a matrix for you of the same size of your drift matrices. If you want to provide custom drift matrices, you would just supply the whole matrix instead. This for gimme argument, in this case, we'll just set it to true. This just creates a long form data set as opposed to a list form data set that I sometimes use for testing. So we've generated our time series. We've generated our true data, or at least our true drift matrices. And so we can visualize what these dynamic models look like as networks, right? So in this case, we're going to use the QGraph function, and we'll look at the dynamic structure implied by the group level model. We'll look at the dynamic structure implied by the subgroup models as well. So here we see the group level dynamics. We see that there are strong autoregressive tendencies. These are continuous time models. Strong autoregressive tendencies for all variables. And then there's a connection between variable 1 and variable 2. There's a connection between variable 5 and variable 3. Every person in our sample has these effects. Then, if we look at our first subgroup, we would see that there are additional paths. So in addition to the 5 to 3 and 1 to 2 paths, we now have a 2 to 1 path. We have a 5 to 1 path. We have a 4 to 1 path. And those are unique to members of subgroup 1. For subgroup 2, we have a path from 2 to 5. We have a path from 2 to 3. And we have a path from 3 to 4. So in this case, there are 3 unique paths for subgroup members, and then there are 2 paths shared by everyone. We've talked about this briefly, both in Sy-Miin's talk as well as mine, but there are ways of transforming these continuous time networks to discrete time networks. And that's because, at least for me, continuous time dynamics are not always intuitive to directly interpret. So for me, it usually helps to transform these continuous time parameters into a discrete time form because it's just easier for me to understand. I learned dynamic networks from a discrete perspective first, and so it always helps for me to go back. And the way that we can transform this network into a discrete time realization is, again, using that matrix exponential. So in this case, if I take the matrix exponential of a times, let's say, 1, I would see what the effects look like at a sampling rate of 1. There are two ways, there's actually three ways to show this. So the first one is to just apply the transformation. You can see here I'm doing matrix exponential of the group level model times 1. And then I'm also doing that for the subgroup level models. If you see this transpose, it's because QGraph doesn't plot things as columns predicting rows. QGraph plots things as rows predicting columns. So you always have to transpose those when you're modeling dynamics. So here, we should see things for people who have fit vector autoregressive models. These are coefficients that are much more understandable. So we have high autoregressions, so but 0.5. And then the effect between variables is about 0.1 to 0.2. So relatively weak dynamics between our variables. And this is, again, to simulate a case that is kind of the most representative of what we might find in psychological data. When we transform for subgroup 2, we see that there are additional paths, again, that were not there previously. We see there's an effect between 5 and 2, whereas the original subgroup path did not have a path from 5 to 2. So just again, we'll see that as you apply this matrix exponential, some paths are going to emerge that were not there in the original continuous time path. That does not mean that these are spurious. These are real effects that are appearing at this particular sampling rate. And then likewise, for the second subgroup, we basically see every single effect exists almost, but they are relatively weak. So you can see some of these are basically 0 within rounding. But we do see complex dynamics emerge from these relatively sparse dynamic networks in continuous time. Other ways that we might choose to visualize the transformation through time might be, in this case, I'm going to create a 2x2 table. So I discretize my continuous time drift matrix by 1/24. So we might think about this as what do the effects look like after an hour? What do the effects look like every 12 hours? What do the effects look like every day? And what do the effects look like every week? So then I might get a plot that looks like this. So we see at a 1-hour rate, basically all of the variables are just predictive of themselves. Every 12 hours, we see the effects are beginning to emerge between the variables. Sampling rate of a day, we see that they're pretty strong now, at least the strongest that they will be. And then finally, we have all of the effects begin to decay or have mostly decayed by a sampling rate of 7. So over the course of a week, this is the evolution that you would see of the effect sizes in the discrete time model. So if I was to fit a discrete time model to data gathered every hour, every 12 hours, every day, or every week, these might be the discrete time networks that I would see for the same underlying continuous process. Different ways of simulating or visualizing these data. So in this case, you'll see code here that I wrote for generating a coefficient plot. So this basically shows the same 5x5 network, but this shows the strength of that particular dynamic association. So from x1 to x1, so this is the autocorrelation. When is it strongest? Near 0, and then we see that it decays. And then this red line is basically the 0 effect. So we can basically see for different dynamics, when are they non-zero, when are they 0? We see for the relationship from x2 to x1, it reaches a peak maybe around 1 to 2 on average, and then it decays, and then we can see all of these different effects. Another thing that we might be interested in doing is generating an animated plot. And so in this case, this is code for generating a GIF or a GIF if you like to say it wrong. And so in this case, this shows the dynamic associations between our variables as we go from an hourly sampling rate to a weekly sampling rate. So you see that autoregressions are very dominant early on. The off-diagonal elements emerge as quite strong in the middle, and then they go back into decaying towards the end of the week. And so this is just another way of visualizing the data. Obviously, for publication, this might be difficult to insert a GIF into your PDF, but it is a nice and helpful way for visualizing how the dynamics are unfolding through time. Finally, for actually fitting a continuous time gimme model, you're going to need specific arguments and specific forms of your data. Luckily, the way that we generate our data are going to be directly how you want the data to look. So if you inspect this sim object, which I'll generate now, if you inspect the sim object, let's look at the head of sim. This is basically the form that we want our data to be in. And so we want an ID variable. We want our variables that we're modeling the time series for. And then we want a time variable. In this case, the time variable should be annotated as a distance from the first measurement occasion. So these should be how far apart is this particular row from the origin. So this is not the first time point. This is how far in time is this time point from the previous one. So this is 1 unit in time from the first time point. This is 2 units in time from the first time point, et cetera, et cetera. And then we just want to stack that. So if I do the tail of sim, you'll see that we have the 20th subject, and then we have the exact same format. So this is the way that we want our data to look like when we're fitting continuous time gimme. You will have to specify the names of your variables, the data set that you have, your ID variable, your time variable. These two arguments for sig thresh and sub sig thresh are going to be the thresholds by which we add parameters. So this is basically saying how many people need to have this path for us to add it to everyone in the total sample or in the subgroup. The G, S, and I alpha are the alpha levels for adding paths at the group level, at the subgroup level, and at the individual level. MEVAR and PEVAR are basically going to be arguments for whether we want to specify a measurement error covariance matrix or a process noise covariance matrix. And then this conduct argument is to force a more stringent but arguably better way of subgrouping. Some of the other arguments that we're leaving out include things like the Benjamini-Hochberg correction. I'm not going to go into that, but that is basically a way that we control for the alpha level. In this case, I'm not talking about it because you should just keep that on always. You should control for your family-wise alpha rate when we're doing these kinds of huge tests. And so we have that as an argument. You will also need a directory. So where are you saving it to? And then we have a cores argument. So fitting continuous time models takes a long time. And so I've made continuous time gimme to be a multi-threaded process. And so then each person can be estimated simultaneously up to the number of cores that you have available. So we can go ahead and fit that very quickly. I'm going to scroll down to the actual continuous time gimme slide. And this is mostly so that I can show folks what the outputs look like when continuous time gimme is running. So you should see here that we are basically going to start running it. I have 10 cores available. And we're going to this should not take long. I promise it will not take long. But it's going to basically scale the variables for the subjects if you choose to have that done. And what we see is it's going to tell you which variable was added. It will tell you the average modification index, whether it was significant for a certain proportion of individuals, and what the Benjamini-Hochberg alpha correction is. And then this is the printout of all of the individual modification indices. So then you can see who did like this parameter, who did not like this parameter. And the way that you would interpret this would be variable 1 predicting variable 2. So this is columns predicting rows. So we're adding a path between variable 1 and variable 2. We're adding a path between variable 3 and variable 5. And then it seems like the variable 3 to variable 4 connection was not significant for a majority of people. So let's stop there. We entered the subgrouping phase. We got the subgroup output. We see that the first 10 subjects are in subgroup 2. The second 10 subjects are in subgroup 1. That's good because that's how we simulated the data. And now we are estimating the data for that first subgroup. And then we're going to basically repeat this process. Luckily, we have already fitted these data, so we don't need to wait. And we can basically explore the results. In addition to this, we also fit the discrete time gimme. So this is there if you would like to check how discrete time gimme works in comparison to the same data. This just formats the data to be friendly for fitting in discrete time gimme, and then you can run this discrete time gimme argument. This uses all of the program defaults of discrete time gimme. But talking about continuous time gimme, you get a series of outputs that you can find in the folder if you downloaded it. So if you come here and you go into first this group paths file, this group paths file is this particular image. And so we label paths as group if they're at the group level. So all of the autoregressive coefficients are group level paths. And then we picked up the 5 to 3 path and the 1 to 2 path as group level paths, and that maps onto our actual true data generating model. For the subgroup level results, we basically see a cluster of 10 people. So 1 through 10 are in this blue cluster. We see 11 through 20 are in this red cluster. Obviously, this is a very clean example. So we get perfect cluster recovery of our simulated data. We can then look at our subgroup 1 level path. So you can see this says SG1. So if you were to click into the models folder and look at subgroup 1, that's where this file is. So we see that the paths we picked up was 2 to 5, 2 to 3, and 3 to 4, and that aligns with our data generating graph for the second subgroup. So we did pick that up, and then I'm just going to just trust me that this one is also correct. I don't want to go into Jex time. We can also look at individual level models. So if we were to go back to the main directory, if we click on models and we click on individuals, you will see that there's a graph for each individual, and there's an RDS object that stores the OpenMX summary output for every single subject so that you can inspect those subjects. If a subject has very crazy estimates, then it's likely the case that something went wrong. And so you can look at their actual OpenMX output, reread the model matrices, refit as you need to. In this case, for this particular individual, we see this structure here, and then we can compare that to their true data generating model. In this case, we see that there are basically downward biases on a lot of the effects, but some of the effects are upwardly biased. So this 4-to-1 connection is upwardly biased, but all the other connections are downwardly biased. But in terms of structural recovery, we did pretty good. To compare this to the discrete time gimme, so this is the discrete time gimme subgroup output for this particular case. So we can see here that subgrouping gimme in the discrete time framework with 200 time points at a sampling rate about 1 unit in time was not able to successfully recover the subgroups. By contrast, if I had sampled this much slower, gimme would do much better because of how information propagates into the contemporaneous effects. But the point that we're trying to drive home is that we probably want our subgroup quality to be relatively stable. We want to tap into the continuous aspect of similarity as opposed to the kind of sampling rate dependent definition of similarity, maybe. And so this is at least the output for continuous time gimme. This is how you would run it. Our output basically shows in R once things are done. It'll tell you where you can find the networks. So in this case, we saved it to this root directory, and then you can find it there. That is it for my portion of this workshop. I'm going to stop sharing so that Jack can do his setup. But if people do have questions, feel free to ask. Also, if you have questions but you're too nervous to ask, you can reach out separately as well via my email.
Let's try to see if there are questions. But if not, maybe we should have a short break. I'm going to ask a question. Jonathan, can
Yes.
you talk about, can you give some sort of insights on how one may set the alpha levels for the group model, individual models, and so forth? I saw that you have different alpha values there.
Yes. So let me check if you're okay with me sharing. In fitting the continuous time gimme models, yes. So I have an alpha level of 0.05, 0.05, and then for the individual model, I have 0.01. So the Benjamini-Hochberg correction that we're running resets at each level. So there's a Benjamini-Hochberg correction at the group level, then it resets for the subgroup level, then it resets for the individual level. And at the group level and the subgroup level, generally speaking, we have enough power to reliably detect the effects, and so then the correction does pretty well. But then at least what I found in testing is that for the individual level models, oftentimes like the noise can subsume, it can appear that there's a very strong effect, and so it gets picked up. And so necessarily I've scaled down the individual alpha levels to be a bit more conservative. But then in cases where I have a lot of individual level effects, this does sometimes penalize that too much. So then sometimes we're recovering really well the group and subgroup level structures, but then if there's person-specific estimates, we might miss those because this is a little bit more conservative. But at least in terms of the smaller sample sizes we tend to get, I tend to err on having a more conservative individual alpha just to not capitalize on noise because we do have this tiered search. Um, yes.
Are there other questions for Jonathan or me or anyone else? Very quiet. So maybe we can go ahead and take a 5-minute break.
Excuse me. So before like a Dr. Peskin to give a presentation, I have a questions for Professor Chow and Professor Park. So can I ask, or should I wait until the end of the meeting?
Oh, please do ask. We were
Yeah.
just,
So
chatting
for
among ourselves why the audience is so quiet, whether it's because some are like at midnight
yeah.
almost, or whether
Yeah, I
so
think maybe it's time to go to like a for participants and think about the questions. Yeah. So for Professor Chow, I remember uh by the end of your presentation, you
Mhm.
mentioned about like the difference between the discrete and continuous case, right? You say
Mhm.
it's A minus, and you said like there's a kind of the sign flip.
Uh-huh,
So
uh-huh.
I just wondered, like, could you explain more why there's a kind of the sign flip?
Oh, it's just the negative of it. So maybe I can quickly share
Oh yeah, I
screen to
appreciate.
go back to um where you were. Hold on. Hmm. So can you see my screen? Okay.
Yeah, yeah,
Yeah. So in discrete time, right? So when we
yeah.
basically write about the var process as fluctuating around the set point, we typically write eta t minus one minus the set point, right?
Oh yeah,
Here you can see that is arranged such that set point is in front, right? So in continuous time, this negative sign here basically makes sure that you move towards the set point rather than going away from it. So then if I were to get this equation into the form of a continuous time state space model,
mm,
which looks like this A right here,
yeah.
then basically there's just that negative sign right here.
Oh, then it become plus, right?
Yeah, yeah,
So
exactly.
it
So
becomes like eta it and then minus this. Wait, so I
exactly.
just wonder, is it like because when you add like a minus, is it because like the eta it plus set points, or like it become like a eta it minus the set points?
So, well, I think this negative sign here again basically makes sure that when you take the matrix exponential, or it may be
Yeah.
easier to think about it as just
Oh, okay.
exponential if you have a single variable, right?
Yeah.
Then basically, if you take like a very large value and then you take the exponential of it, right? Then it basically makes sure that you have no movement anymore, and then you basically stays at the set point.
Okay. Okay, I
Yeah.
see. Yeah,
Yeah.
yeah.
So then this negative sign is just
Mm.
there to make sure that basically, over time, right, large amount of time, then you basically goes towards the set point.
Oh, okay, I see. Yeah, yeah, yeah.
So
Thank
then the intercept in this case actually is a function of the set point,
you.
and this drift matrix, the negative of the drift matrix. And
Mm.
then the drift matrix, the transition matrix is basically just minus of this one.
Okay, I see, I see. Okay, okay, I appreciate it. Yeah. And for Professor Park, I remember at the beginning of your presentation, you mentioned about like the delta t. I remember you mentioned like delta t equal to 0.5, delta t equal to 1, right? It's the third or fourth slide. And then you shows what is the relationship between the depression and anxiety. Can you show that slide for me?
Yes.
Yeah.
Let me pull that up. Apparently I don't have it. Let me,
Take your time.
yes, there we go. I will share screen now. All right, so you're talking about this slide, right?
Yeah, so my question is, I understand what you talk about, but I'm just curious. So, for example, at effect at the delta t equal to 0.05, the relationship between depression and anxiety is the 0.19, right?
Yes.
So I just wonder why when you increase the time to the delta t equal to 1, the relationship becomes stronger, but when you go to the effect at delta t equal to 7, it becomes weaker again. I'm just curious about that.
Yeah, this might be best shown in this plot, right? So when we're applying the matrix exponential, we're not just kind of we're not monotonically increasing the effect size. And if you
Oh,
want to think about um, at very small intervals, the best predictor of the next value of your state is just the same variable at the previous time point. And so at very small delta t's, you'll see that it's almost always dominated by the autoregressions. And so then
okay.
it takes time for any kind of information from other variables to propagate to the variables. So there's this period of growth where slowly the effect of one
Oh,
variable on another
okay.
increases, but then after enough time has elapsed, then it's going to start decaying again because it's just no longer being meaningful.
Oh,
So you have this kind of curvilinear relationship between the two.
I see, I see. Yeah, yeah, that totally makes sense. Okay, thanks so much. Yep.
Yeah, yeah,
That's
yeah.
my question. Yep. If audience have any questions, feel free to drop in the chat box and we reply as soon as possible. Thank you so much. Yep.
Tell me when it's actually my turn. Hi. Okay, sure. So, hello. Can you see my screen?
Yes, I can see you.
Okay. So I'm Jack. I'm currently a postdoc at Penn State, but starting this September, I'll start a new role as assistant research professor. This morning I'll talk about dynamic mediation models. Okay. So okay. Mediation models are actually very popular. Like if you do like a Google Scholar search, you see like millions and millions of papers that actually use mediation. And if you're familiar with mediation, it was popularized in psychology by Barron and Kenny in the 1980s. And it was first popularized in the context of like a cross-sectional mediation model where you actually measure all the variables at the same time. So for example, in this particular example, we have variable stress, X, coping, M, and variable Y as mood. And they're basically measured at the same time. But in this particular model, we situate these variables such that we are actually saying that X stress has an effect on Y mood through a mediating variable M, which is coping. In this particular example, which is cross-sectional, we only have a single snapshot of all the variables measured at the same time. So the narrative is just, it's like, if you think about it, it's just one picture of the associations between these variables at a given time point. It's very static. There's no dynamism in it. Okay. Eventually, there's like development in the methods that we do. So if we really want to see or make conclusions about directionality of these effects, we should like model them in sequential snapshots rather than just one single snapshot. So a better version of that mediation model is this three-wave longitudinal mediation model, where stress is measured at wave 1, mood is measured at wave 2, and then what's this? Coping is measured at wave 2, and then mood is actually measured at wave 3. So this is a little bit better because we have like sequential snapshots. You can think about this, for example, when we measure stress in the morning, we measure coping in the afternoon, and we measure mood, for example, in the evening, and we can actually see like a certain sense of dynamism in terms of how the effects of one variable on another unfolds over time. So this is better than the previous one, but we only have like 3 snapshots of the process. There's some dynamism to it, but probably not enough to be able to really like describe the process that we are actually interested in. We can think about it in terms of like a discrete time vector autoregressive model that previous speakers have already talked a lot. In this particular example, we don't just have 3 snapshots. So for example, if we're measuring stress, mood, and stress, coping, and mood, let's say, for example, every day for, let's say, for example, 30 days, or if we have like a more fine-grained way of doing that, let's say, for example, we're measuring it every hour. So we can think of it as like many, many pictures of the process. And I don't know if you did this when you were a kid, like you would draw on like a notebook, like scribble something on one page of a notebook, and then scribble something on another page of a notebook, and then scribble something on another page of a notebook, and then you flip it, and you actually see like, oh, it's moving. There's dynamism in the associations. The associations between these variables are actually evolving across time. Okay, so basically we can think of the associations between variable x, m, and y as evolving across the different snapshots that we're actually able to do in the way we actually collected it. Let's say it's daily, for example, it's hourly, for example, whatever time intervals that you're actually interested in. Okay, so here we see, for example, the effect of X stress on and M coping and Y mood as unfolding across the discrete time measurements that we are actually able to gather. Okay, this is so much better than the cross-sectional and also the 3 time points because we can actually see like motion, but it's still a flip book. Jonathan alluded to the assumption that we have that these variables are actually associated in changing across continuous time, right? So instead of just having a flip book, the reality is that these variables are kind of like, you think about it as motion pictures, like movies, like very smooth movement of the association. So we can actually do better from the flip book by like watching a movie and seeing how these 3 variables actually unfold, or these 3 variables are actually associated with each other. So Sy-Miin and Jonathan actually talked about continuous time vector autoregressive models. So basically the idea is that even if we're not measuring the same variables of interest, we can think about them as like, oh, there's like latent variables in between our measurements that these variables are actually continuing to unfold over time, independent of the measurement intervals that we're actually using in this particular in our particular study. So you can think about this as like a movie where instead of having that flip book in a movie, you say let's say this analogy is still discrete, but you have like 20 frames per second, where it's the movement of the people in the movie is actually very smooth. And in this particular example, we can actually see like a smooth trajectory of the associations between these particular variables. So we can measure the tempo and the rhythm of change between these particular variables. We can actually see, as alluded to by the previous speakers, how these effects that we're actually interested in unfold and change over time and eventually dissipate. Okay, so instead of thinking of the time interval dependency in discrete time models as a problem, we see it as like as a feature of the phenomena that we're actually interested in, that they actually change across time. And if we are able to model things in a continuous time framework, we're actually able to show how these associations actually change across time. So here, let's go back to the example of having stress and coping and mood. X as stress, coping as M, and mood as Y. So the red line, the red curve, is like the indirect effect of stress on mood via coping. The purple is the total effect, and the blue is actually the direct effect. We can see that in the short term, let's say like less than an hour. So stress direct effect, actually it's kind of negative. Okay, so the direct effect is negative, and it's actually dominating the associations between stress and mood. Okay, so like coping hasn't, you can think about it, coping hasn't worked yet at the initial hour, for example, less than an hour. But in the medium term, for example, let's see around 2 to 5 hours, we can see that there's already like an increase in the indirect effect. Okay, meaning that the associations between stress and a mood is actually starting to be like mediated by your coping. Okay, so it sort of happens medium term. Okay, and then in the long term, eventually the system stabilizes. Eventually, the direct, indirect effects, and the total effects they go to like a specific equilibrium, and then they eventually go to zero. Okay, so in this particular graph, we can see like the associations between these variables, the direct, indirect, and total effects. We can clearly see that in this particular graph that these are actually changing. And these are actually like dependent on the specific time intervals that are actually that we're actually looking into these particular variables. And this particular dynamism gives us like a richer understanding of the associations between these variables that we're actually looking at. Okay, clear so far? Okay, so how do we think about total direct and indirect effects in the context of continuous time mediation models? So let's say, for example, in the 3-variable example that we have X predicting Y. And then in this particular, like I'm using like a discrete example because like I cannot think of like an infinite number of latent variables in between, but hopefully like the discrete example will actually be able to help us understand what's going on in the continuous time mediation model. So we have variable X, which is stress, affecting mood at a particular time interval. Okay, it can be any time interval, but in this particular example, have like a delta 3 of 1, 2, 3, 3. Okay, in this framework, we think about this as like the total effect. This is the total effect of this particular variable X stress on this particular variable Y mood. So the idea is that there's a lot of effects flowing from here that reaches this. So you can see that there are like different possible paths, right? Different possible paths from here to here. So this is like the total effect. And then the idea is that we decompose the total effect into what is direct and what is indirect. Okay, the idea is that we take a look at all the possible paths where our mediator variable of interest is crossed, and we actually define that as the indirect effect. This is one example of an indirect effect. And we take a look at paths where the mediator variable of interest is not crossed. Okay, so we define that as the direct effect. So in this particular discrete time example, these are all the possible paths from X to Y that I've traced. All the red paths actually crossed the mediator variable of interest, which is scoping. So we call those red paths as indirect effects. And all the blue paths did not cross the mediator variable of interest, and these are actually indirect effects. So the idea is that, okay, we sum up all those indirect effects to get at the indirect effect of coping on the association between stress and mood. We sum up all the direct effects to actually get at the direct effects or the direct associations between stress and mood. Okay, how do we do that in continuous time? So we do that like the previous speakers have already talked about it in great detail. Sorry for the difference in notation. In many situations, the phi is actually used as a matrix for the lagged associations, discrete time associations. But in the paper that I wrote for this particular topic, I used phi as the matrix, the drift matrix, which is like the associations that we can see in the continuous time framework. So again, the idea is that we use a specific time interval, and the idea in a continuous time mediation framework is that the total indirect and direct effects are actually defined across different time intervals of interest, and you can actually create like a fine grain of like specific different time intervals of interest to actually see like how these particular effects actually unfold. So the idea is that, similar to the example a while ago, it's basically just getting sums of the direct and indirect effect as we actually defined it in this particular discrete time example. Okay. It's also helpful to actually think about how do we actually standardize these effects in psychology and the social sciences. Most of the time we deal with like standardized regression coefficients, for example. So it's easier for us to actually interpret these effects if we're able to kind of come up with like a way of thinking about them as effect sizes. And we can actually do that also in the context of continuous time mediation models. Like we can use the standard deviations of the variables of interest to standardize the effects that we're actually looking at. Clear so far? Are we good so far? So the idea again is that if we take a look at the x-axis here, we have time intervals from 0 to 10. And then we have, time intervals in between the discrete numbers. And you can see you can actually generate like a smooth curve of how the effects actually unfold in continuous time. And again, it introduces more of the dynamics about how, like if you can think about regulation, you can think about, the effects of stress, etc., in terms of like interpreting how these changes actually change across different time intervals. So far, we're okay? Okay. Okay. So that's if you're in psychology and the social sciences, that's fairly straightforward because we always have a lot of like these mediation models, right? We're like looking at like specific paths. We have specific hypotheses about how the variables actually line up cleanly in a mediation model, right? So for example, in our example, we have like stress, coping, and mood, and it's cascading that way. And we have a lot of those examples. But we can also think about continuous time mediation, like from a network perspective. Okay, we can think about continuous time mediation from a network perspective. And in a network perspective, instead of just taking a look at, single mediated pathways, for example, we can take a look at system level summaries of how effects actually spread throughout the system, right? So Jonathan has actually shown like a lot of graphs of like very interesting things where like nodes are connected, and like you can like in my mind it's like there's like effects flowing. Like the way I think about it is like there's effects flowing in the system. Yeah, we have like single paths that we're familiar with and we use a lot in psychology. But I think it's also important for us to actually take a look at like how in the system level how these effects are actually flowing around the system. Okay, and from how we defined total indirect effects from a continuous time mediation model, we can use those ideas to think to come up with like system level summaries of the associations in the model. So one system level summary is the total effect centrality. Okay. So the idea is the question that this particular metric asks is which variable matters most for shaping the rest of the system over time. So if you take a look at this particular diagram, you see like, oh, this particular variable is actually very much associated with many of the actually all of the variables in this particular example. So total effect centrality is like, okay, what if I sum up all those total effects to get at a metric that shows which variable matters for shaping the variables in the system? Okay, so that's basically total effect centrality. Okay, another perspective that we can actually think about is like, because like this is mediation, right? So in the social sciences, we know that the associations between variables are not really just straightforward, like one variable predicting another. In many situations, it's like it's cascading and there are like variables in between. So that's why like mediation models are actually very popular because like, it's like these effects are unfolding across like not just time, but like associations between different variables. Okay. Another system level metric that we can use is the indirect effect centrality. It actually asks the question, which variable matters most as the pathway through which effects spread across the variables over time. So in this particular example, we can see that this variable here is kind of like a node where variables would actually pass through and then go to another. Okay. So its relevance is not so much in its direct association with the variable's interest, but it's become like a conduit in which specific variables that are in the system are actually operating in terms of like influencing the other variables in the system. Okay. So when I started looking at this, it's like it's kind of like a different perspective with what I'm used to, because like I'm used to like mediation models where you have like theoretical ideas about like tracing specific paths and like having hypotheses about those specific paths. But this perspective is a little bit different in a sense that we're still thinking about those specific paths, but we're aggregating them and thinking about the importance of the variables in the way we actually aggregate these particular system level like metrics of like importance of the variables. Okay, so far? Are we good so far? Like don't hesitate to like ask questions if you have specific questions. So basically, this just kind of like defines it. It's basically summing up those effects. So the perspective from a centrality measure perspective is not just the individual paths, but like the aggregate of those. In a way, we actually ascribe importance to the specific variables in the system. And we define the importance of those in terms of like the total effect, and we define the importance in terms of like the indirect effect. We define it in terms of like how one variable has like an outward effect on the variables in the system, and that's total effect centrality. And then in the context of indirect effect centrality, we quantify how a particular variable is a conduit of the associations between the variables in the system. Okay. That's well and good, but it's actually important for us to like quantify the uncertainty associated with our estimates, right? So it's not enough in the social science. It's not enough for us to actually say, oh, we have this effect, we have this total effect, direct effect, etc., etc. And we can see it here, right? Like we can just plot it like this. But also we have to actually be able to quantify the uncertainty associated with these particular estimates, right? So we have contributed to this field by introducing, different ways of quantifying uncertainty via standard errors and confidence intervals. We have introduced the delta method, the Monte Carlo method, and the parametric bootstrap approach. So the delta method is like when you zoom in to like a particular parameter, for example, and when you zoom in enough, it's like it's a line. It's like a linear approximation of that particular effect, right? And then you can actually using that approximation, you can actually say, or you can actually quantify how certain or uncertain that particular parameter is. So the Monte Carlo method, on the other hand, is if you're familiar with the bootstrap, it's very similar to the bootstrap. The idea is that, okay, you have estimated parameters, right, from your model. And then the idea is that you use those estimated parameters to generate a distribution of other parameters, such that you can actually get like standard errors by getting the standard deviations of those simulated parameters. And from the distribution of the simulated parameters, you can actually create confidence intervals. Okay. The difference between the Monte Carlo method and the bootstrap is that in the Monte Carlo method, you do not require refitting the data many, many times, which can be computationally expensive, especially in the context of continuous time models. So parametric bootstrap is actually similar in the sense that we're using the estimated parameters from our model, and then we generate data from that parametric model, and then we refit the model, let's say, for example, 1,000 times. Okay. So in the mediation literature, like the bootstrap is kind of like the gold standard, but in the context of time series, continuous time models, basically dynamic models, it's just very expensive to actually refit the model many, many, many times. So the compromise is like the Monte Carlo method, which is like in the middle between the delta and the parametric bootstrap. So here we're still able to sort of like through replication and resampling, we can generate a distribution of effects, but we don't have to actually refit the model many, many times. Okay. And we have shown that the delta method is okay for smaller time intervals, but when your time intervals are actually starting to be relatively large, it starts to fail. And I guess the idea is like the linear approximation becomes very difficult when the time interval is actually getting bigger. So the matrix exponentiation it's not very linear such that the linear approximation doesn't really work that well. Parametric bootstrap works very well, but it's really very computationally expensive. The Monte Carlo method works really well, and it's feasible. You don't have to spend 4 years writing one paper for if you use the Monte Carlo method. It's like in a few minutes you actually get results. Okay. So one way to actually visualize the uncertainty associated with the parameters of interest is to create what we call regions of significance. Okay, so basically, in this particular example, we have the total effect of stress on coping, which is like the purple line here. The one in the middle is like our estimates across different time intervals from 0 to 10. And then we create confidence intervals in between, like we create like a lower bound and an upper bound that kind of sandwiches our estimates as a way for us to quantify the uncertainty associated with those estimates. So if your confidence intervals are wider, you have less uncertainty associated with your effects. If your confidence intervals are kind of narrower, you have like your uncertainty is better. So we introduce regions of significance by kind of like introducing like color to it. So for time intervals where the confidence intervals contain 0, there's no color. So you see here, there's no color, there's no shading. But for time intervals where 0 is not contained in the confidence intervals, you can see shading. So how do we interpret this? So for time intervals that are around, let's say, 0.7 or something, like we have significant results until that time. But then from 0.7 up to, let's say, 4.2, it's like, it's not significantly different from 0. And then the effects become significant greater than 4 until 8. Okay, that's a way to actually look at like the regions of the significance in this particular example. So if you're familiar with like moderation analysis, for me, like it's not quite accurate, but you can think of time as a moderator and think of the effects changing as you're actually changing the time intervals that you're actually using. Okay. If you take a look at the direct effect, this one is pretty straightforward. So all the effects that we actually plotted from 0 to around 10, delta t of 10, time interval of 10, they're all statistically significant. You can see that like all of them are like have like colored regions. So the regions of significance are like, okay, just everything from 0 to 10 is statistically significant. But still, you notice that the effects also change, and also like the uncertainty. So you have you see here like you have more uncertainty when time intervals are actually larger, as opposed to like when time intervals are actually smaller. So if you have like substantive interpretations for that, you can actually include that in your analysis. That adds up to the dynamism. It's not just the the effects changing, but the uncertainty associated with those effects actually are also like interpretable in that sense. We have very similar results for the indirect effect. Okay, but this time it's like it's positive. So from 0 to -10. Okay. So far, so good. We're okay. So what can we take away from like the conceptual understanding of these things? Okay. So the key takeaways are like mediation unfolds dynamically in time. Like even if the method started as like, like in the cross-sectional field or in this, like just measuring things at the same time. When I think of mediation, I'm always thinking about like, what's the process? What's the dynamic process involved? There's always, for me in my mind, there's always like the directionality of effects. There's always like how effects actually unfold across time, right? So it's like for me, it's like you have water that flows and water needs like time to actually flow. So the continuous time mediation perspective gives mediation back that idea of like how to actually think about these things from a dynamic perspective. So cross-sectional gives us associations, not dynamics. Discrete time approximates the dynamics with fixed intervals, but it depends on the chosen sampling rate, chosen delta t, the time interval. Continuous time mediation generalizes this idea by recovering how effects emerge, propagate, dissipate, regardless of the measurement spacing. So we can actually move from just snapshots to motions, to averages, to mechanisms. So these are actually like the hypotheses that we have in our substantive fields. And using the continuous time mediation framework allows us to actually, map out more closely our theories to how we actually analyze the data and how we actually interpret the results of the data analysis. So continuous time mediation shows how total, direct, and indirect effect change with time when mediation is strongest and how long the effects actually last. So in the graphs, we can see, okay, it peaks at the particular time and then it dissipates after a particular time. And also that the time intervals are actually important as well, because like it's not gonna like in many cases in psychological data, like those time intervals are actually very important. It's like the associations between variables in psychology don't really last forever. So, but it's important for us to get to see like what particular time intervals are actually very important, where the effects actually become high, if that's actually the important thing in your particular research, when the effects become low, and when the effects actually dissipate or go to zero. So these things we can see, we can actually clearly visualize, and we can actually take a look at the uncertainty associated with these effects using the continuous time mediation framework. We have also introduced like a way to standardize these effects to sort of help us in terms of standardizing like the effects that are a little bit more interpretable as we are actually familiar with like standardized regression coefficients. So we added inference and regions of significance. And also I like the idea of thinking about this from like a network perspective using total effect centrality and indirect effect centrality. Okay, so all of these, the visualization, the calculation, they're all in the cTMed package. It integrates all the computations for effect sizes, generating confidence intervals, plotting how effects actually change across time, looking at the uncertainty quantification. They're all in the cTMed package. And let me just go through the kind of like the package documentation, and also go through some examples. Okay, let me just. Are there questions so far? Are things clear? If there are things that need to be clarified, you can just blurt out and ask. Can you see my screen? Okay. So cTMed, this is the GitHub repository for cTMed. In the materials for the course, I have links to all these. And this is available. I updated it for this class, actually. I sent an update to Cran so that you get the most updated version of this. There's an accompanying web page that has all the functions in the package and some articles that you might find useful. So for example, I have articles about how to fit a continuous time vector autoregressive model in dynr and OpenMX. So there's an example here. I don't know if I'll have enough time to actually go through all this, but everything is there. And also you can email me if you have questions about like how to fit these things. So in my work, I've been using dynr and OpenMX, so that's why I put dynr and OpenMX here. But if you're familiar with the continuous time literature, you might actually find ctSem as a way to actually fit continuous time models. ctSem, the original ctSem uses OpenMX under the hood, but there's an expanded version of ctSem that uses Bayesian statistics using Stan to fit the continuous time model. I don't have an example up here, but Charles Driver has a lot of like examples in his GitHub repository for the ctSem package. I also
So
have example. Yes.
So, Jack, I'm not sure how many participants are already familiar with dynr and OpenMX. They may not be, right? And I saw that the code example that you uploaded to the course website kind of, uses dynr.
Yes.
So maybe, when you go over it, can you kind of, go over it with the assumption that if someone has no idea at all on how to use dynr, but they want to fit a VAR model with a minimum modification to your code, what
Yes.
are the key absolute minimum things that they have to change?
So in the course materials, I also uploaded like a file like called empirical. It's just that I couldn't just share the dataset because I don't have permission to share the dataset. But the my intention was to go through uh like how I actually fitted the model using an empirical dataset, and then how I actually uh went about estimating the total direct and indirect effects. So I'll go first through the code that I used to fit the continuous time vector autoregressive model. Can you see my screen? Is it like big enough? Let's see.
Maybe larger form is better. Yeah. Yeah.
Yeah,
That's
see.
good for me. Yeah.
Okay. So I used the I used the ADID dataset, which is actually a dataset that was collected by Sy-Miin. Were you at Notre Dame when you collected? Yeah, or UNC?
This is at UNC, yeah, but you
Oh, yeah.
can actually share the data set, or
Okay.
maybe you can describe, what the input data set would look like for someone who is kind of using this.
Okay. So the ADID dataset is a dataset where there's an EMA component where individuals were actually like asked. I think it's like every 6 hours within the like four times a day, right? Like if I'm correct, 4 times a day. And then there are specific questions that have to do with our positive and negative emotions, personality, stress, and other variables that are, the idea is that these variables are changing, and we want to actually like measure them across the days through measurement across like 4 days. No, 4 days, four times per day. The way I did it, I cleaned up the dataset a little bit better by using the actual timestamp that was used in the data collection. So I did not use like the 4 days as kind of like a discrete time point. So I was like, okay, this particular person answered this particular question at this particular time. And that sort of created like an irregular time spacing between the responses. So if you're collecting data, my recommendation is if you're collecting it digitally, get information about the timestamp. It will save your butt in many situations because you can actually see like, oh, when are the individuals actually responding to the questions? So so based on the time, there's like irregularity in it, and then I just allowed the irregularity because continuous time vector autoregressive models allow for them. But I just created like a transformation to the time variable such that the average time in between the measurements would actually be close as possible to one. So that the delta t unit of one in my transformation is approximately 6 hours. So if you have like delta t of one, it's like approximately 6 hours. So I just did that for to help with the optimization process.
So to reiterate, Jack, to make sure that the participants understand, if you scroll up a little bit in your script, right? So you're saying that basically what you're fitting in for model fitting purposes is a long or relational data, right? Where you have a column for participant ID, and then you have multiple repeated measurements, for each person, right? So the time column basically has the actual time values, right? They can take on real values, like from 0 to like 0.1, 0.2, 1, 2, so forth. They may be irregularly spaced, but it reflects whatever time units, right, or scales that you're interested in. And then you have the observed variables, perceived stress, emotional stability, and negative affect, it seems, right, as the remaining columns. I also it sounds like you also have utility functions, right, for cleaning up and rescaling the time units to facilitate convergence. So I assume that these are all available on the GitHub page.
Yeah, so they're available. I'm not yet that confident with the utility functions because I still have to make changes. I haven't submitted it to CRAN, but they're available in GitHub. But at the moment, I have to double check whether they're actually like accurate, very, very accurate before I submit it to CRAN. And I don't want to be like the reason why you guys have like errors in your data
So
analysis.
maybe you can just kind of reiterate again, what are some of the consideration
Yeah.
or manipulation that people tend to need to do in terms of rescaling, thinking about how they rescale the time?
So the first is that to aid in optimization, apparently like the optimizers want, because of you remember that when we do matrix exponential, we're multiplying it with time, right? The time interval. It's easier to do the exponential if the time interval is 1 because you don't have to multiply because it's just exponentiating the drift matrix. So it's very helpful in the optimization process. It doesn't change like the meaning of things. It just changes the unit of time that you have. So in this particular empirical example, I got like the average such that the time interval is actually 1 at around like approximately 6. That's one consideration. Second consideration is that for each individual, you have to make sure that you have information for the initial time point. Okay, so like that's one of the things that I was like having problems before, like, oh, it's not working. Then I looked at the data. It's like at the beginning there's no information, so there's no information to begin with. So it's important to take a look at your data set and see at the beginning of like your time 0, like the beginning, like, do you have information from your for that specific participant or that specific
They are
ID?
not all missing data
Yeah,
across all
yeah,
the variables.
yeah.
Mhm.
That's very important. Another thing that actually helped for me is that, especially in terms of calculating standard errors, it's not so much about optimization, but it's actually getting a good Hessian, is what's called in the literature as like oversampling. So you have information at the beginning, right? But you can insert like missing data in between to actually kind of like pad your time interval. So let's say, for example, uh, you get like you insert like a row for time interval for time 0.1 and then another row for time 0.2, so on and so forth. Okay, so it doesn't really help in the optimization process per se in my experience, because I've been able to fit models even without oversampling, but it definitely helps in the calculation of standard errors, which is what I actually need to generate uncertainty associated with the effects. So oversampling is like, it's not imputation because you're not introducing any information. You're just inserting missing data in between your time intervals to get like a finer time intervals. Again, it's in my experience, you can get estimates even if you don't even if you don't oversample, but it really helps in the calculation of the Hessian, which helps in the calculation of the standard errors. So other than that, I think it's also very important to have a lot of familiarity with your data set to see like peculiarities. And it helps to be able to actually plot your data set to see if like there's like, you know, abrupt changes in the information. Okay. Another thing that I did, which just came to mind, is Sy-Miin mentioned in her talk that it's possible for the set point to be changing, right? It's possible for the information to have like a trend. In the example that I have here, I made sure to like remove the trend so that it's actually just the effects are actually just going around like a stable point without a trend. Okay. So I can read in the data. And my computer's not cooperating. Okay. So for the measurement part, Okay. What's this? Sorry. Okay. So for the measurement part, you can actually specify, if you're familiar with like CFA, if you're familiar with confirmatory factor analysis, you can actually specify like a measurement model, and then you actually have like indicators actually measuring those like your latent variables. Let's see. So, okay, so basically what I'm actually trying to do here is that I have single indicators of like my latent variable. So I have one measurement of perceived stress that is actually used to measure a latent variable perceived stress, and so on and so forth for the rest of the three variables. You cannot do this in continual and in conventional CFA, but you can do this in the context of time series models. So you can actually have in the context of like a state space model, you can have like a single indicator for a latent variable. So again, apologies because I used phi as a symbol for the drift matrix. Basically, let me run this so that you can actually see. So basically, I have three formulas here corresponding to the three latent variables: stress, emotional stability, and negative affect. And then basically, I have phi number, which basically the first number is the row, and then the second is the column in the drift matrix, multiplied by the latent variables. So basically, you have your drift matrix and then a vector of your latent variables. I did not have the set point here because I basically just removed the trends and removed the person specific differences by centering within individual. So I didn't at this particular example, I didn't need to actually model the means because I basically removed them in the data preparation. But in many situations when you have substantive research questions associated with these, it's kind of like important to also include, let's say, for example, a random what's this set point that Sy-Miin actually mentioned earlier. But here you can basically see you have a drift matrix, which is basically distills the associations between the variables and then basically just multiplying them by the latent variables. In dynr, I find that it's very crucial that you think about good starting values for when you actually do the optimization process. If you have not so great starting values, it can take too long to actually fit. And sometimes if your starting values do not result to like a drift matrix that's stable, you can actually have like problems. In this particular example, I just used for the auto effects, the auto-regressive effects, the effect of a variable on itself, I just used negative 0.05, and then the rest I actually just put 0. Now, if you're doing this in your actual research, you will probably do this like not just once, you will refit the model many times. And in a sense, you get you get a sense of what good starting values are after like running it several times. So you can learn from your own model refitting to actually think about, okay, what you think is actually good starting values. So here, because I've already refitted this, I know that these are actually relatively good starting values. Like even if I just put zeros in the off diagonals. Okay. In the way I parameterize things, the auto effects, I specified it as kind of like negative. So instead of multiplying it by a negative value, I offhand it's just negative for me. Like the cross effects are actually just negative for this particular specification. But you can also do it either way. and then you prep the formula basically. So basically, if you are familiar with the LM package, the LM function in R, what we're doing basically is creating a formula in the same spirit as the LM function. So this one is basically in the same spirit as the LM function.
So Jack, I think, we only have like about 15 minutes left, and I want to make sure that, you get to the cTMed part,
Yes.
right? The mediation part, which is
Sorry.
ultimately, what people are interested in here. So
Yes.
to kind of quickly summarize, right, what you say, your current script, 000 CTWAR, and I like that, I think Jack has this way of ordering his files so that it starts from 000 to 001 and so forth. So basically 001 gives a script, right, for fitting continuous time VAR model using dynr, but someone else may, use OpenMX or other programs for doing this. But ultimately, what we need, extracted from there would be what Jack calls the phi matrix, right? What I call the transition matrix that has the sort of matrix of, ARs and CR in discrete time, or here, because it's in continuous time, it's basically that drift matrix, right? So it looks like, in your code, things are pretty automated, right? In the sense that the key things that people would need to change, if you scroll down a little bit, would be the names of the observed variables, right? To make sure that they match, right? What you have in your data set. So scroll up a little bit more, right? So in Jack's data sets, basically, his observed variables are called, so can you go to your observed variable names? Yeah, so he actually in his data set would have perceived stress, emo stable, PANAS, NAC as the observed variable names. Like these variables have to exist in his data set. And then the state names are the names, for the latent variable counterpart, like the names of the nodes, which he called stress, instability, and NA. So then if you're trying to fit a VAR model of other dimensions, let's say if you have 4 variables, 4 dependent variables, then make sure that you have like 4 of these in this instead of 3. Your observed variable names have to match what you have in your data set. Your latent variables, you can call them whatever you want. Another thing that Jack also highlighted there is, basically for the cross-process couplings, he set starting values to be 0, basically assuming no cross-coupling across processes, right? And then he used negative starting values for the continuous time models. So this basically makes sure that, you approach the set point of 0 because he used detrended data. Other than that, other than changing the dimensions of the input variables and so forth, like people can basically use, right, the code as is to fit whatever VAR model of choice, correct?
Yes. And another thing that I want to point out is that it's also important to add optimization bounds to the parameters. So it comes with like some familiarity with your data set. So for example, if you don't expect, your drift matrix to be like super, super large, like 100, like you can bound the optimization so that the process would actually be a little bit faster. Yeah. So let me see. I will just extract. So basically what you need from the fitted continuous time vector autoregressive model would be the phi matrix, which is basically the associations between the variables. And because I'm using the standardized version in terms of calculating the total direct and indirect effects, I also need the process noise covariance matrix sigma. So basically, you need to extract the phi, which is the associations, and then the process noise variance covariance matrix. At the same time, you need to put them in a vector as theta, and you need to actually extract the sampling variance covariance matrix. Basically, if you're familiar with like standard errors are the square root of the diagonal of the variance covariance matrix. You need to extract the entire one because we're actually saying that effects are not independent from each other. So they're also associated. So once you have those, you can specify delta t values that you want. Okay, so I specified here some landmark values that I think are important. So 0.5 is like one half hour, 1 hour, 3 hours, so on and so forth. And then I create like a delta t vector. Okay, this delta t vector is actually it's overkill in my opinion, because it's like, I think it's like 1,000. It's 1,000 data points, but I just wanted to actually fill out all the specific time intervals. Note that this is still discrete, because you still have like discrete values, but it's like it's small enough, it's close enough such that you can, you can actually visualize like very, very small changes in the delta t to visualize the dynamics. So because I scaled in the model fitting, I scaled the time to approximately 6 hours. I just wanted to convert to that when I actually use the time intervals. But then again, in the plotting, it's still 1 unit is still approximately 6 hours. So one of the things that I want to be able to do in the future is add like arguments to the plotting function to sort of rescale the data in terms of the time interval that you want, so that you don't have to be doing all those calculations of like, oh, 1:6. So hopefully in the future, I can actually add that functionality that will allow you to actually, plot the results based on the time intervals that you're actually interested in. So here is the function. So because I'm using the standardized one, I'm using cMed std for the standardized version. You can still also use the delta method, but Monte Carlo method is the preferred. Again, you have the drift matrix, you have the diffusion matrix, and you have the sampling variance covariance matrix of the drift matrix and the diffusion matrix. I'm using the delta t that we created, like this 1,000 plus vector. The important thing for like the path specific perspective is you have to specify where is the effect coming from and where is the effect going to. So the to and from are always a single variable. But the mediator is either a single variable or many variables. You can actually have like multiple mediators. So in this particular example, my from is stress, my to is instability, and then my mediator is negative affect. Okay. R is basically just the number of Monte Carlo replications. Test phi is to make sure that the drift matrix that we're generating is stable. Diag sigma is that if your process noise covariance matrix is actually just diagonal, you can actually specify, okay, I just have a diagonal process noise covariance matrix. N cores is the number of cores. Because this can be computationally expensive, it's a good idea to actually specify many cores. Seed is just random seed because this generates data. It's good to have reproducible results. Tolerance is that it's not gonna do 0, because if you multiply a drift matrix to 0 and get an exponential, it's not gonna work. So tolerance value is like the smallest value for a time interval. So I put here 0.001. So from 0.001 until like the largest time interval, which is 12. I'm not gonna run this because this might take a while to run, but I'm actually reading in the result. Please work. Sometimes when my computer heats up too much, this happens. Oh, there. Okay. So this will give you MC. Oh, let's put it MC. Okay. So once you get MC, you can do a summary if you want to see the numbers. This can take a while because it's a lot. I think this is overkill that I have so many time intervals. But I just wanted, like, for me, it's like, I just wanted to do it because the plots are actually nicer if it's very smooth. Okay, so basically you have, it's very long. So you have your effect, the time interval, the estimated standard errors, the number of replications, and then the confidence intervals. Okay, so it's total direct and indirect effects across 0.0001 until it's not even printed in. But an easier way to do it is just plot it. Plot. Again, apologies, my computer is kind of heating up a little bit. You can do this. Come on. There you go. So these are like very similar to the ones that I actually have in the example that I presented in the slides. The only difference is that there's not much total effect from stress from stress to emotional instability, but there is indirect effect passing through negative affect in this particular example. Okay, so if we do total effect centrality, the idea is the same. Also, the process in which you actually generate these plots and these numbers are the same. It's just that instead of tracing it from to via a particular mediator variable, you're aggregating total effects and you're aggregating indirect effects. Okay, so let me just read in a total effect centrality results. Okay, and then plot that. So this will be, you have a specific plot, one plot per variable in your system. Okay, so each particular variable has a specific total effect centrality value. And then you can actually compare those total effect centrality value to make, judgments about how, important those particular variables are. So this is the total effect centrality for negative affect, total effect centrality for instability, and total effect centrality for stress. So in terms of the total effect of stress, it's mostly zero. So the effect of stress is actually, if we take a look at the indirect effect centrality, so the total effect is basically how each variable is has an effect on the rest of the variables in the system, and basically just aggregates that. The indirect effect is how each of the variables are conduits of the associations between the variables. So for the indirect effect centrality, let's wait for it. If you have questions while there we go. There we go. Okay. So also stress is not a good indirect or mediator variable across the different variables in the system. Instability is, but it's only statistically significant until around 6.5. You multiply that by times 6 to get the hours. And then negative affect is actually it's a good mediator of the associations between the variables of interest. Okay. It becomes a little more interesting if you have more variables in the system to actually really see if I take a look at this particular example, this particular variable, it's this is a very good indirect effect centrality measure. This is a variable that's a very good conduit between the associations of the variables. So if you want to read the paper that we wrote for that, I also have a link to the repository for everything that we did. If you want to reproduce everything, you can. You can do everything that we did. There's a repository for that as well. And feel free to actually send me emails if you have questions about the topics that we have discussed today.
Yeah, thank you so much for your presentation, and thank you so much for Professor Chow, Professor Park, and Dr. Pesigan for a wonderful presentation about a package and how to use it, a topic. So, any audience have questions, please feel free to reach out to them after the workshop, or you can unmute yourself or drop your question in the chat box right now.
Yeah, actually, I have some quick questions.
Sure, go.
Yes. Yes. This question is for all three faculties here, doctors here. And um, on the slide, we learned that discrete time transition matrix V can be converted to continuous time A matrix. And I understand converting from CT time A matrix to V matrix is always possible, but converting from V matrix back to A matrix is not. So could you explain why this conversion always work in one direction but not necessarily in the other? So
A
let's
question
say
for all three of us, right? So any of us can
yes,
answer.
yes.
Yeah, so basically in continuous time, right? So we need to know the delta t, right, in
hmm
order to get things there. So
hmm
if you have the continuous time, drift matrix, and you know the delta t, right, then you can always convert things to sort of discrete time.
hmm
But if you kind of already fit the model in discrete time, and then you want to convert things back, then you don't have the information that you need unless you make some other constraints to allow you to do the mapping.
Since we only know one single time, delta t, so we cannot convert it to the continuous time matrix, right?
Mhm.
Uh-huh. And the other question is, we learned that in this DT model, the stability check is requires all eigenvalues of transition V matrix to have like less than one absolute values. Then is there any stability check in continuous time modeling in terms of drift A matrix? And
Yeah,
how can
so
we?
so in the R Markdown code that I shared,
Mm-hmm,
I basically give examples of how to do stability analysis check in discrete time and continuous time. So
mm,
you should get the same results, right? You can always, do stability check for continuous time, for example, by looking at the eigenvalues, right?
mm-hmm.
The real eigenvalues from your drift matrix. And then if they are negative, then you basically have stable system. And then you can also do
Ah,
equivalent tests by converting your continuous time drift matrix into the discrete time transition matrix, and then do the same check. You will have the same conclusions.
so kind of eigenvalues of A matrix. If we have negative values, then it should be converged, right?
Yeah, then it should go
Uh-huh,
towards the set point. And then if you have complex values, it would go towards the set point in a spiral way, right? Instead of like
uh-huh,
this way, right?
I see.
Um,
Am I? Yeah.
just to add to the first 2 points that Sy-Miin has covered, there's always a way of doing the matrix exponential of your drift matrix, but going the opposite way, doing the matrix logarithm of a matrix is not always possible. And so even if you have a discrete time matrix and you do know what your sampling rate is for certain drift matrices, you can't take the matrix logarithm. So you can't back transform the discrete time matrix into an
Mm-hmm.
analog of the continuous time one.
Ah,
On the basis of the stability check as well, there's something to be said about the how much of the time series you actually have, right? So mathematically, you can have a stationary time series in continuous time where the eigenvalues are all negative. But if you only sample a small subset of that time series, in one that is nearly explosive, but mathematically never quite does so. If you sample too small of a window, you can have a period where it's kind of going up And in the long form, if you did get a big enough window, it's going to kind of oscillate back and forth, but never explode.
Mm-hmm.
But if you only get a small window of that, it's going to look like your time series is going up. And so then it's
Mm-hmm.
going to appear locally non-stationary, despite the fact that mathematically your drift matrix is stationary. And so if people do use my functions for generating drift matrices, I actually have a threshold argument where the eigenvalues have to be both negative, but also sufficiently negative. So like eigenvalues of like minus zero point 0.2 or something.
Mm-hmm.
And that's just to make sure that you have like stationary time series at even arbitrarily small lengths. But there's this going to be this interplay between how much of the overall process you have and whether it's stationary. Like it's always going to be stationary if the eigenvalues are negative, but it might not look like it if you have too small of a window.
Oh, I see. Yeah, thank you so much. And my last question is quite naive one. After hearing this workshop, I feel like indeed it is very helpful to answer the questions by using continuous time modeling rather than discrete time one. But if two studies use different sampling intervals, then it is better for us to use continuous time modeling. But as an alternative, can we, using the transition matrices of two different study to find common time scales before comparing them in practice, those kind of approaches are quite appropriate, or rather go with the continuous time? Do you guys recommend just go with the continuous time modeling?
So there's literature in the meta-analysis field. They call it
Mm-hmm.
COTIMA, basically continuous time meta-analysis.
Mm-hmm.
So I mean, from that particular literature, the idea is that you convert first to like a continuous time perspective, and then
Mm-hmm.
from there you can do the comparisons to whatever time intervals like that you have. At
Ah.
least from that particular literature, that's what
Mm-hmm.
they think about. But there's also like problems about like matrix logarithms and stuff like that. The approach that Sy-Miin and Jonathan actually have in the book chapter in the Handbook of Structural Equation Modeling, I've played with the approach. They're better than matrix logarithms. They're able to actually what's this get at uh, the the conversion better because like matrix logarithms are kind of very brittle,
Mm-hmm.
but still there are, if you're really interested in the topic, maybe you can actually review that particular book chapter again.
I see. And
So I
uh,
think
mm,
ultimately the starting point is that, the different studies and papers need to report and make available, right, the delta T
mm-hmm.
values that are being
Mm,
used.
mm,
So if two papers are indeed both fitting discrete time, VAR
mm-hmm.
type models,
Mm-hmm.
then in principle, you can still convert, the parameter estimates to the same timescales. If you know that for this study, they use every hour, and another study, you use 6 hours.
Mm-hmm.
You can do the conversion yourself as long as you have the information available in terms of
Mm-hmm.
what time scales are being used in the two studies.
Mm-hmm.
Also related to this, I have a project that's ongoing that
Mm-hmm.
basically, right. So if I measure you every day for 30 days, I've also measured you every other day for
Mm-hmm.
15 days.
Mm-hmm.
And so I'm actually I have an algorithm that will basically circumvent the matrix logarithm by not doing the matrix logarithm. But it's basically, can you fit progressively crappy VAR models to data and use the estimates and the uncertainty of those estimates to find the drift matrix that would intersect the points that you would get had you fit those discrete time models. And it's
Mm,
showing to be somewhat decent at large effect sizes. And so that's another way where, reflecting on Sy-Miin's point, if people were very transparent about the sampling schedule that they're following, then you would, in theory, not only be able to use this approach, we're calling it CFDT, But if you use this approach, then you could plug in different studies at these known sampling rates, and then you're trying to find the drift matrix that, when exponentiated, because the exponential always exists, would intersect the var parameters at those different points. And so then if you can find some sort of common trend, it shows that it does work pretty well.
I see.
And then you avoid the complexities of fitting the continuous time model. So you kind of get, so you kind of get the continuous time drift matrix without having to do it. But it is relatively fragile, so we're still testing it.
I see. Thank you so much for the workshop and the kind answers.
Thanks for the questions.
Any other questions?
May I have one? So it's a question to Ivan Jacob. Thank you for your presentation. Of course, everybody is excellent, but I have a question to you. So presumably that we are analyzing stationary time series. What if we are interested still in supporting some trend analysis? Is it possible?
I think it's possible by modeling the trend itself. So for example, you can actually model the set point as actually time varying. So in my opinion, like, correct me, Sy-Miin, if I'm wrong, like if I'm able to account for the trend by modeling a set point that varies across time and across individuals, I'm able to actually account for the fact that there's a trend in the series. So basically the idea is that instead of the variables actually moving around one set point, the variables are moving in a set point that changes across time. You can add, Sy-Miin, if you want.
Okay, accepted.
Yeah, indeed, I think it would be, if you have the option to simultaneously model the trend and the fluctuations around the trend, that would be best. If not, then at least taking a sequential approach where you first remove the trend, by fitting a model that captures the growth curve of interest, or you do differencing, to get rid of the trends before you fit the model to the residuals, would be recommended. There's, I think, one paper that I included in the resources part towards the end of my slides that has a paper, and also it has code for fitting this kind of model simultaneously that has the trend integrated as part of a VAR process with random effects, and then fitting to panel data. This is done in JAX, so the code is a bit longer with all the priors and so forth, but it's available for anyone who's interested.
Thank you very much. And one notion to Jonathan Parkham's, I somehow failed to find your PDF presentation in a Academy website. Should I try harder?
It should be there, but if you cannot, let me see very quickly if I can just do this. So within this folder, I know that it's complicated in how it's laid out here, but if we were to download this, you can see there's this ISDSA.
Okay.
Yes.
Okay.
So that would be the
not so far.
presentation
Okay.
slides. Yeah.
Thank you very much. Thank you. Thank you, all of you. Best.
Thanks for the question.
Thank
Can
you,
I ask a
everyone.
question to Jack? Yeah,
Go
right.
for
So,
it.
Is this
I know
about the
that,
aesthetics of smooth
yeah.
curves?
I know that Young Won, when she was doing her comprehensive examinations, was doing a lot of readings about like optimal timescale. So the idea being, one of the definitions being like, when is the effect very salient or very strong, such that this is the sampling rate that one might want to pick? And plotting both that and the uncertainty made me think, is there a way of operationalizing this such that you try to find the optimal sampling rate where you balance the magnitude of the coefficient, but also minimize the uncertainty? And do you think that those are necessarily going to align? Right. So then can you leverage that to help pinpoint like a good sampling rate if I had to kind of decide on a schedule?
Yeah, I think Peggy has a paper on that. Basically, the idea is like finding the maximal effect, but I'm not sure if she integrated uncertainty. So that's a brilliant idea. But my starting point would be I would apply Peggy's approach, and then find a way to actually integrate uncertainty associated with like how Peggy actually did it. Nice, very very great, nice idea. Yeah. Because like it can be like, like high, but then your uncertainty is like very
Yeah.
wide, right?
It's like it could be 0.01 or
Yeah.
it could be 0.9.
Yeah. Any last minute questions? Okay, if no, thank you so much for our speakers today. One more round of applause. And also thank you so much for participants for joining. I know in some time zone it's pretty late. So take a good rest and wish you guys have a good day. Okay. Bye everyone. Bye.
Bye, everyone.
Goodbye, everyone.
Bye.